Hello, everybody. Welcome to the first day of UCF workshop. We have really exciting agenda for all 3 days. Our original plan was to make it a hybrid event with in-person and virtual participation, but I believe we're still in the times of COVID, so it's difficult for people to travel for a variety of reasons. So as the last years, this event is fully virtual. And as for today, again, we have 3 days of the event. I will quickly scroll all the agenda. We have between 4 to 5 hours for each one of the days. First and second day of the event focused on UCF projects, specifically UCX, collectives, projects around DPU and so on. And the last day of workshop is mainly focused on OpenSHMEM programming models and talks about OpenSHMEM. We're hosting our friends from OpenSHMEM community on the last day of the event. All the agenda is available on our GitHub page. So if you go to UCF or to GitHub, you can link the page. And there's information for each one of the talks. Roughly speaking, we have a break every couple of talks. I believe every 2 or 3 talks we have a break. You're more than welcome to stay on the call. We have lunch break somewhere in the middle to give people time to eat something. And I believe our first presentation for today is by Gilad Shiner from NVIDIA. Gilad will talk about deep dive into DPU computing, addressing HPC, AI, and performance bottlenecks. I will stop sharing the screen. Gilad, feel free to take it over, and I will continue to read your bio and introduction.
Yeah, maybe just a little bit overall. So we used to run the UCF workshops in December, 2-3 weeks after supercomputing, and we did so for several years, and now we changed to September. We do consider to move it back to December next year, to do it after supercomputing. If someone has, by the way, any sort of feedback on timing, we definitely appreciate to hear about that. But I think for next year, we're probably aiming to go back around December and probably try to go and actually do it hybrid. Location is still to be defined. So that's on that part. The second part is during the first 2 days. The third day is, Pasha mentioned, it's dedicated for OpenSHMEM. The first 2 days, we're going to touch on different kind of topics. Some topics related to development, pure development. The other part going to be on usage of UCC, UCX, and so forth, as part of full platforms that folks build. That will be my topic for today and for tomorrow. So there's another session tomorrow. Feel free to ask questions. I know that folks are muted as you join, but feel free to ask questions. You can use the chat or at the end of every session. Beyond of that, there is several working groups as part of UCF. They're dealing with different areas. So obviously there is UCC and UCX and UCC, point-to-point and collective communications. So development there is ongoing. Folks are more than welcome to join, by the way. If there's anyone interested to join and participate and contribute, that's great. The other working group around creating a benchmark suite, which is HPCA, and other activities. So with that, I think we covered the intro. I want to thank Brian and Gabby for helping to facilitate the Zoom and everything around that, and for Oscar for his great help to build the infrastructure that needed in order to submit all the proposals and run everything and help to combine OpenSHMEM and UCF days together. So thank you very much, folks. I probably missed some others that I need to thank you, but we'll probably can do that in the last session of the workshop or the conference. And I think Yossi is also here. Yossi is going to present after me. Just checking. Yossi, you are here, right? I think I see.
Yes, I am. Hi.
Just in case I'm gonna finish a little bit earlier, it's good that you're here, so you can start. And worst case, we'll have a little bit longer break. So with that, I'm gonna share my screen. Brian, Gabby, anything else related to administrative portion?
No, just like what Pasha said, we do have a couple breaks throughout the day, so give you some time to get some lunch, some food, check some email. So we look forward to having a great conference here.
On additional note, as Gilad trying to get his slides up, all the talks will be video recorded, and eventually we will share everything on UCF YouTube channel. Typically it takes at least between a couple of weeks and months for us to get everything processed and uploaded, but eventually all the talks will be video recorded and published as well. Whenever it's possible, we're trying to get slides from people and share the slides on the UCF website as well. Well, let me introduce Gilad Shiner. Gilad Shiner serves as Senior Vice President of Marketing for NVIDIA Networking, focusing high performance computing, artificial intelligence, and InfiniBand technology. Mr. Shiner joined Mellanox in 2001 as design engineer, later served as senior marketing management role since 2005. Mr. Shiner serves as the chairman of the HPC Advisory Council organization, the president of UCF and CCIX consortium, and member of IBTA organization contributor to PCI SIG, PCIX, and PCI Express. Mr. Shiner holds multiple patents in the field high-speed networking. He's a recipient of 2015 R&D award for his contribution Core Direct in network computing technology, and 2019 R&D 100 award for his contribution to the UCX project. Gilad, the floor is yours.
Yeah, it was a long intro. Well, I should have cut it. He's shorter. Thanks, Pasha. So I'm gonna talk about DPU computing, and I'm gonna try to focus on part of that. There is another session tomorrow that will talk about performance isolation, which I'll participate together with Jitin from Microsoft Azure, and that will address another part of DPU computing, which is related to performance isolation on a multi-tenant or a multi-job environment. So today I'm going to focus more on doing the intro on DPU and discuss one area around what we can do with DPU as a computing platform. So first looking from a high-level perspective and kind of talking about the main reason for building DPUs, or the main reason to create a DPU, which is a new computing platform in the data center or in HPC platform. So over time, with the increase of HPC applications, increase of users that sharing the same supercomputing infrastructure. The overhead that the infrastructure workload imposes on CPUs or GPUs continue to increase. And looking ahead, as we see that HPC workloads, such as AI and others, are increasing, and we see increase in users and entity that need to have access to supercomputing infrastructure to run their HPC workloads. The infrastructure workload will become the most complicated workload in the supercomputer, most complicated workload in a data center. And that means is that its overhead on the CPU or the GPU will continue to increase. Today, we're already seeing the toll. So the overhead of communication libraries, overhead of MPI or SHMEM or Nickel, for example, or other communications, not necessarily those ones, start to take a bigger and bigger toll on the CPU. So we cannot utilize all of the cores in the CPU, for example, and some of the cores on GPUs cannot be utilized as well. So actually, we start losing compute capabilities. Overhead of storage, if it's the effect of file systems on CPU performance due to jitter, due to overhead, and then also security and isolation. Now, not all of supercomputing infrastructures need security and isolation today, but definitely all of them will need it in the future. If we want to host more users, if you want to increase collaborations between industry and supercomputing centers, with the increased usage of AI, there will be more commercial companies looking for supercomputing resources to use, and so forth. And therefore, we will need to bring security and isolation into supercomputing in order to facilitate access for commercial users, for example. And even among users that are not necessarily in commercial space, we will probably need to bring more isolations between them. And it's not isolation on the node, on the server per se, but it's also isolation on the network, or isolations on accessing storage, memory, and so forth. Now, in order to eliminate this increasing overhead from the CPU or from the GPU, we actually need to bring a new computing platform for that infrastructure workload. A new computing platform that is not connected to the same host memory, a new computing platform that will enable to isolate the infrastructure domain from the computing domain or from the application domain. An infrastructure that can deliver the compute infrastructure that can deliver the right platform for the infrastructure workloads. And that's the DPU. That's a data processing unit. So the data processing unit, essentially, you can look at that as a new generation of networking. If we had a kind of quote unquote standard NIC and then become a smart NIC, and now it's become DPUs. So you can look at that on evolution of networking infrastructure. On the other side, and that's how I look on that, the DPU is actually a new computing platform. A new computing platform in the data center, a new computing platform in the supercomputer. And this new computing platform has been designed for the infrastructure workloads. It has been designed to enable security and isolation. It has been designed to support storage, to support disaggregated storage, to support NVMe, to support file systems, for example, manage access to file systems. It's designed for communication frameworks. It's designed to run MPI, SHMEM, PGAS, Nickel, and so forth. It's designed to be the most effective compute platform for the infrastructure workload. It's not just adding a bunch of compute cores into a network device and call it DPU, but it's actually building dedicated hardware engines that sits around programmable cores which also combine with the network device itself to actually form a platform that is suitable for the infrastructure. So in my perspective, or in our perspective, we look on the DPU, it's a new computing infrastructure, new computing platform in the data center. And that means that now we have three computing platforms. We have CPU on one side, GPU on the other side, and the DPU, which is the new entity here. Now with the DPUs, we are working on 5 areas that improve application performance, improve the infrastructure management, improve the infrastructure capabilities, and the things we can do on supercomputing platforms that we could not do before. So the first one is in-network computing. Now we started with in-network computing a while ago by adding the ability to do reduction operations on the switch devices. We started with that by migrating few engines that can help with MPI tag matching and so forth. But with the DPU, we are now introducing essentially multiple programmable cores. Part of those are ARM cores running standard Linux. The other part is it's an array of data path accelerator with an MMU. So that actually there are 2 kinds of programmable computing infrastructures that provide capabilities to program the DPU to perform different kind of data algorithms, obviously. So this is one area, and we're using that in-network computing, we're using the cores through the SDKs that are being built and the services that are being built to migrate, for example, MPI operations to be managed and executed by the DPU. So that enables, for example, to move non-blocking collective operations. It also helps to move the blocking collective operations. That helps to move point-to-point communication and so forth. And with doing that, by actually enabling the DPU to provide UCC and UCX services, running on the ARM cores and provide that to the MPI processor that's running on the host. And I'll show you some examples around that. I'm going to go into more details in that area. Another area is storage, or computational storage. And here the DPU can actually enable to do multiple things. First, when we're talking about file system or block storage, we can migrate the file system process or the block storage processes running on the host, running on the CPU, to run on the DPU. By doing that, and knowing that the DPU can access the host memory directly, so there is no need, not necessarily you need to copy data into the DPU memory and then copy the data from the DPU memory to the host memory. The DPU can actually access directly using memory keys the host memory, so you don't need to do copies. And with that, an ability to move the file system or the block system processes to the DPU, we can reduce the overhead on CPUs, obviously. We can also reduce the jitter effects that file system processes are doing on the CPU. The DPU can pretend to be a local NVMe, local SSD. And with that, the DPU can actually present itself as an SSD to the application running on the host. Actually, it can present itself to be an unlimited size of SSD. So with that application access or use the DPU as a local NVMe. And on the other side, the DPU translate all local NVMe command to remote NV command, send them on the wire to actually access NVMe over fabrics, accessing JBOF. So you can bring disaggregated storage, disaggregated NVMe, use a remote JBOFs, remote NVMe platforms and have the DPU, the ones that manage access to those platforms on one side, and another side pretend to be a local NVMe to the application running on the host. You can add to that the ability to offload storage checksums, to do compressions and decompressions, for example, and you actually get a strong new platform for all the storage activities that you need. So that's the second element. The third element is around performance isolation. And performance isolation, when we talk about performance isolation, we mean the ability to make sure that the platform that hosts multiple users or multiple jobs concurrently, that one job will not impact another job performance. How it's being done and performance results around that, that's something that we will present tomorrow. We also present first results running on Azure, which is a kind of a multi-tenant platform, so it can take things into the extreme from that perspective. Another area, it's enhanced telemetry. DPU as a compute platform can be a device that actually collect telemetry information from all of the components of the data center. So it's not just network telemetry, but also information from CPUs, information from GPUs, and it can do that at zero cost. Instead of having the CPU collect information or telemetry information from the server, which actually costs in the CPU performance, here the DPU can do it by itself. So it's a zero cost. With collecting that information, the DPU can actually do some interesting things. For example, we can create correlations between process IDs and the IO that those process ID generates. If you take it to the next level and collect that between multiple DPUs running on multiple nodes, you can actually create correlations between a job and how much IO that job generates. And as you can generate something like that, to create something like that, to learn something like that, you can actually start looking into doing job placement or job scheduling, not just according to how many nodes the job requires, but also how much IO that job requires as well. So that's a new concept and something that we don't do today. Today, when we're scheduling jobs, it's pretty much based on how many nodes they need, how many CPUs or GPUs they need, but that's it. The reason that we don't do it also according to how much IO they need is because in most cases we do not know. We do not know. So the DPU can actually help us to get good estimations on how much IO jobs consumes. And with that, we can actually do better placements of jobs. And then last and not least is security. So if we plan to host more users, if we're seeing the need from the industry, from the commercial industry to access supercomputing infrastructures, and we'll see that need increases over time, we will need to bring abilities or capabilities of security into the data center or security into the supercomputing platforms. But it's not just isolating on the node, because we can say that we just give one node per job, or we don't give less than a node to a job. We still need to make sure that a user accessing the server is not able to access or take control of the infrastructure. So at least we need to separate between the infrastructure domain and the application domain. So we need to move the infrastructure domain to a new device outside of the CPU. And actually, the DPU is a great device to do that. So by moving the infrastructure workload to be managed by the DPU, we bring first levels of security by isolating the application domain from the infrastructure domain. Now, we can go into higher levels of security here. The DPU has the capabilities of encrypting and decrypting data. So the DPU can create encrypted enclaves inside of a supercomputer. And to decrypt and encrypt data that comes in and out from that encrypted enclave, to secure data that goes to the storage, and so forth. So moving data centers or moving supercomputing platform towards a zero trust infrastructures. And we will see the security requirements evolve over time. And we will see that we will need to bring more and more security into supercomputers. And the DPU, it's a great device to actually do that without impacting overhead on CPUs or GPUs. So if we look at the entire networking infrastructure from NVIDIA perspective, it includes the switches, obviously, and what we have on the switches is data reductions, what we call sharp, the ability to use the switch to do reduce and no reduce and bear and broadcast, for example. And by doing reductions on the switches, we reduce the amount of bandwidth you need to use for reductions by half. That's on one side. On the other side, as the switch fabric is much more immune to system size, we can also get flat latencies for small message reductions. ConnectX is the NICs, and ConnectX it's actually being replaced by the DPU. So the DPU includes all of the ConnectX functionality inside, beside of the new computing platforms, and therefore the Bluetooth or the DPU devices will become the de facto NICs in the future. There are also gateways to connect between InfiniBand and Ethernet, to connect between the InfiniBand system, the InfiniBand HPC pod, the InfiniBand supercomputer, to the data center or remote Ethernet access, and of course, full suite of management tools. Now, as we look on the DPU, just to give a more clear view of what the DPU is or what the DPU consists of. So this is a large view of a DPU. This is a picture of Bluefield 2, second generation of DPUs of NVIDIA, but it resembles the third generation, probably resemble other DPUs in the market. So in Bluefield 2 includes all of the ConnectX inside. ConnectX, it's the full NICs. All of the network functions of the NIC is part of the DPU. Bluefield 2 includes ConnectX 6, which is a 200 gig device. Bluefield 3 includes ConnectX 7, which is a 400 gig device. Next to the ConnectX, next to the NIC IP, there is multiple ARM cores in our case. Bluefield 2 includes 8 cores. Bluefield 3 includes 16 cores of ARM 64-bit A78. So that's and running full Linux, running Ubuntu, for example. There are several acceleration engines that, combined with the ARM cores, make the DPU the best infrastructure processor. So there is acceleration engines around communication libraries. There is acceleration engines around storage. There is acceleration engines around security, engines around telemetry collections, and so forth. There is also a data path accelerator that includes 16 cores with an MMU that sits on a data path that can do quick changes of incoming or outgoing traffic, or inject traffic or create traffic. There is a memory interface, a DDR memory interface, and there is memory on the card itself, and PCI Express switch. This PCI Express switch gives the capabilities to first add more PCI Express lanes to the system. The second, to be able to connect to other PCI Express devices. For example, we can plug a flash device through that PCI Express switch to the DPU and increase memory or storage capacities. We can plug a GPU directly to the DPU, and actually the GPU power sits behind the DPU itself. You can create cards that has GPUs and DPUs and forms and accelerated cards for data center infrastructures and so forth. Now, the differences between Bluefield 2, which exists now, and Bluefield 3, which is sampling shortly, is first increasing the data bandwidth. So today, Bluefield 2 supports 200 gigabit per second. We're moving to 400 gigabit per second with the integrated ConnectX 7 inside Bluefield 3. Message rate is going from 215 million messages per second to 370. On the compute side, looking on spec int 17 from almost 10 to 42. So there's a good increase in the compute capacities and also in the memory bandwidth. Bluefield 4, which it's a future device, will obviously further increase. So looking at doubling the bandwidth, increasing the compute, increasing memory bandwidth, and so forth. Now, it's not just, as I mentioned, not just the ARM cores or the data path accelerator. The integrated ConnectX bring full transport offload and telemetry into the DPU. Hardware-based capabilities of GPU Direct as well, not just RDMA. So GPU Direct, RDMA, GPU Direct storage. The engines around MPI and nickel accelerations. So it's not moving things to the ARM cores, but it's utilizing the services, utilizing the SDKs, and of course utilizing the dedicated hardware engines. I mentioned computational storage, compressions, decompression, checksums, NVMe emulations, and I also mentioned some of the security engines. There are different kinds of, there's key management, there's encryption, decryption, another limit around security. So there is a multiple hardware engines that combine with programmable areas of 16 ARM cores A78 and a data path accelerator to actually form this new computing platform. Now, the way that it works is first for development, you can simply SSH into the DPU. The DPU, it's a full computer by itself. So by plugging a DPU inside of a server, you actually get a new computer inside of the computer. You can easily SSH into that. It's running Linux, and you can use it as a new computer in the infrastructure. In a production operations, not necessarily you want to give access to every user to SSH the DPU and run its own code, but you want to see directly because the DPU is an element that can actually provision the server. So in this case, the DPU will actually provide services. So what we do from NVIDIA perspective, we provide Docker. And Docker, it's a set of libraries and runtimes that runs on a DPU. And on top of that, you can provide services. You can create services. Services for UCX, services for UCC, services for other implementations of MPI, for example, a nickel service, a file system service, a block storage service, and so forth. And the processes running on us can actually call those services and have the DPU to perform those services instead of locally accessing the DPU directly from a user perspective. The DPU has its HPC network, for example, running InfiniBand here and connected through a UFM management into the cloud orchestration. The DPU also has a 1 gig for management. That management network can be connected to so forth. And if you want to ensure that no one can access the DPU, you can have a separate management network for the DPU, and through that, you manage the DPU and you manage the entire infrastructure. Could be Omnia, which could be any commercial version, and so forth. Now, the main bottlenecks that we are using the DPU to actually bring solution for first is the synchronous progress, or asynchronous progress actually. So in order to utilizing non-blocking operations, for example, non-blocking collector operations, you need another compute infrastructure to do that. Having dedicated or taking some cores of the CPU for MPI to run non-blocking operation doesn't really work. Doesn't really work because on one side, I'm actually losing cores that I can use for the compute side. On the other side, all of those cores sits on the same memory complex. So even though I can have separate cores to do a non-blocking operations, they still sitting on the same memory of the other cores. So that's present different kind of issues. So with having the DPUs as the entity that progress MPI operations, we can actually move and support asynchronous progress and leverage the DPU to achieve overlapping between compute and communications. Another area is load imbalanced. And the DPU can help doing that by first more balancing jobs being distributed on the server itself. On the other side, it can also progress MPI algorithms, even if other nodes are busy from a CPU perspective. So if I'm running different kind of MPI algorithms and cases where CPUs might be busy and cannot directly answer those algorithms, actually the DPU can do that instead. And by doing that, it can enable progress of the MPI communications, even if some nodes are still busy on the CPU side. Jitter is another area. For example, the file system process jitter that is being created on the client side. So having the DPU is the one that manage all those operations and able to eliminate or reduce the jitter. And also performance interference between jobs. We can use the DPU as actually to solve that problem. And again, that's something that we'll discuss more tomorrow. So from a services perspective, DPU comes with the SDK. SDK, it's full set of libraries and runtimes that enables to use the DPU as a computer by itself. And on top of that, as I mentioned previously, we bring services. And not just services that we create. For example, we enable UCC services or ECX services or Nickel services on the DP itself, but it's also enable others to create their own services. For example, we're working with DK Panda on bringing MVAPIC service on the DPU. You can do other MPI services running on the DPU. Storage services or any other user-defined services can be created, loaded on the DPU, and then the DPU can provide those services to the application running on their host. A simple example, how we move any sort of communications, point-to-point or collective communications to the DPU. Essentially, the DPU receive the metadata from the host, indicating on what kind of operation is required or what kind of service is required. From that point, DPUs first would communicate between themselves. So the DPU, for example, in rank 0 will send information to the DPU in rank 1. If it's ready to get data and give him the right attributes, the DPU in rank 1 can perform RDMA operations with memory keys. So it can access any memory on any node, in a sense. So in this case, we're actually doing read operations, and for the DPU on rank 1, we perform a read operations from rank 0, having the memory key from the other DPU from rank 0. It will perform the read operations, receive the data, put it on the host memory, and then acknowledge back to the initiated DPU that operation is completed, and then the DPU can acknowledge send on rank 0 that the full operations were completed. So essentially, the DPUs can manage and perform all of communication operations between hosts, directly accessing memory, the host memory. Obviously, they have their own memory as well, and with that, migrate point-to-point and collective operations, which could be blocking operations or non-blocking operations. So here is an example of all-to-all-V. So looking on latency of all-to-all-V, we're using the OSU benchmark here. 1 ppm on the left side and 32 ppms on the right side. Looking on 32 nodes, you can see the difference of running the operation on the host, kind of standard, or moving that all-to-all-V operations to be done on the DPU in the same algorithms or kind of the same concept that I showed in the previous slide. We see the nice reduction in timing here, nice reduction in latency. And of course, as we have more nodes, the impact will become bigger and bigger. So this is the all-to-all-V. Here's the example of high all-to-all-V. So looking on the asynchronous all-to-all-V latencies, and obviously when you have non-blocking operations, the gain is going to be higher. So here again on the left side, you can see the performance advantage of the DPU. 1 ppm on the left side and 30 ppm or 32 ppm on the right side. Now with migrating all of the multi-process, not just multi-process, also point-to-point operations to the DPU, we're also obviously enabling full overlap between compute and communications. You see that on the right side again for 1 ppm, and on the left side for 1 ppm, on the right side for 32 ppms. On 1 ppm on few nodes, you see that's kind of growing from almost 70% to reach almost 100% overlap. On a 32 ppm, it's kind of 100% overlap. Not dependent on the system size. So it's a huge increase in overlap, and with that, we of course can for application that utilizing non-blocking operations, we can completely hide those MPR operations from the host side or the timing from the host, and with that to be able to improve application performance. So there's several areas. Of course, we're focusing on the MPI, migrating MPI operations down to the DPU and have the DPU provide those services. And with that, testing different kind of applications. Molecular dynamics work was done by Georgia Tech, work that was help funded, supported by Sandia National Labs. Here they didn't use MPI, but they actually took MiniMD and moved part of MiniMD algorithms to run on the DPU in parallel of having the other part of MiniMD to run on the host. So that's what they did. On mathematical modeling, for example, FFTs, it's a work that was done between Ohio State Universities and San Diego Supercomputing Center, taking the 3-dimensional FFTs, which was based on blocking all-to-all operations, and change FFTs to the 3-dimensional FFT to run on non-blocking or to use non-blocking all-to-all operations, and with that to be able to leverage the DPU for that non-blocking operation. And then we are working with a weather entity, weather and climate entity, on a code, climate distribution code to actually also leverage a DPU. And here it's not just for non-blocking operations, but this is for blocking and non-blocking multi-process synchronizations. The results that we've seen so far was 20% on mini-MT, was 26% on FFTs, and almost 25% or 24% on weather forecasting. So those are a few examples. We will release more examples for more applications, but obviously as moving MPI and having the DPU provide those MPI services, that will enable a good range of scientific applications to improve their performance. With that, what do you say? A few words. So we are enabling UCC and UCX on the DPU. From NVIDIA perspective, that will be released next month. So that will bring the capabilities of UCC and UCX services on the DPU. Working with NVAPIC. So the work that was done on NVAPIC wasn't utilizing all of the capabilities of the DPU. Still, with NVAPIC, there is a copy of data from the host to the DPU. We're working with DK Panda and the team there to leverage the DPU capability to access the host memory directly. So with that, we're expecting to see another nice performance with NVAPIC, and of course, helping this team to bring an NVAPIC service to run on the DPU. So there is no need to do SSH to the DPU, but actually accessing the DPU through a secured communication channel and actually enabling NVAPIC service on the DPU. There is more work around different kind of elements. We will be conducting, by the way, if anyone interested, we will be conducting a DPU HPC hackathon in October, together with several entities, with a UK entity, the Iraq entity, that will provide detailed tutorials on how to utilize in the DPU, as well as ability to access DPU platforms and perform different kind of experiments. So if there is anyone interested in joining the DPU hackathon next month, please do let me know, and I'll connect you to the right information. So with that, I'm gonna stop. Stop sharing to see if there are any questions I can answer.
Hey, Gilad. There are a couple of questions online. I will start with question in the chat. Do you see DPU as a building block for software-defined HPC infrastructure like the virtual cluster models that CSCS has talked about for the successor to PSDIND? Can DPU provide platform for resource management across virtual clusters and help solve resource availability and utilization problems?
Yeah, you can use the DPU for that, right? You can use the DPU to separate elements, disaggregated services, for example, separate storage and separate other infrastructure items. So the answer is yes. The answer is yes for that. Essentially, it's a new computing platform, right? And I think we're right now touching only the first things that we can do with the DPU. So the disaggregated elements, the separating, the creating big building blocks, the storage part, MPI and nickel services, we will see more. We are seeing teams from different kind of supercomputing centers actually coming with their own usage of DPUs. And those hackathons are actually great opportunities to actually explore the DPUs to do more. I see there's another question. So what kind of ARM cores does the Bluetooth 3 have? So it's ARM A78. There are 16 cores of ARM 78. So I see that question on the Q&A part.
Okay. I don't believe we have any other pending questions. Reminder to attendees, you can post your questions in Q&A section of the Zoom, or you can use chat to post your questions. Probably will prefer Q&A, single place, it's easier to track. If you have any more questions, feel free to post it right away or even later, and we can reply some of the questions offline. Gilad, thank you very much for presenting. Your time was your own spot.
Thank you.
Okay, our next speaker for today is Yossi Itigin. Yossi, good job on getting your slides on time for sharing. Let me introduce Yossi. Yossi is a co-maintainer of UCX. Yossi is UCX team lead at NVIDIA, focuses on high-performance communication middleware, maintainer OpenUCX project. Prior to joining to NVIDIA, Yossi spent 9 years at Mellons Technologies in different technical roles, all related to developing and optimizing RDMA software. And in this presentation, Yossi will cover a very exciting topic, UCX protocols version 2. For those that not aware, UCX going through major redesign for the protocol layers in UCX, and this is pretty much what Yossi will be covering in his talk.
Thanks, Pasha. So, hello everyone. And as Pasha said, we're going through major redesign. It's been a while, about 2 years now, that we're working on this, and seems like we have most of the work done. The major goal of this redesign is that, contrary to the previous situation where all the protocols were part of some monolithic code base and there were common functions that handled all the protocols, we want to separate protocols definition that is specific for every protocol from the logic that actually selects which protocols to use. And we want to build the protocols independently from one another. And we want to have a common infrastructure that can be reused between the protocols, but not necessarily enforce some specific behavior or design that is imposed on all the protocols. In addition to that, we can reuse the existence of common infrastructure to extend our debugging and tracing utilities, so we'll know what happens. Often we get questions like, which kind of operation is my application doing? Is it using eager, rendezvous, RDMA read, or RDMA write? Which kind of device is being used? Am I using a pipeline protocol? And so on. Or even a more complex question like, why am I doing eager or why am I doing rendezvous right now? In protocols V1, we had some mathematical formulas that used to calculate the threshold. But in this case, we're taking a different approach that we estimate the performance of each protocol independently and then select the best one for each range. And the new thing we added this year is the ability to trace the selection process up to the smallest details of every performance estimation of every little component to understand if we really have a problem and why is that. So the new protocols also can account for different data types, topology, in this case, server topology, and operation flags. We have several flags like multi-send or fast completion, and we can add more. And every kind of operation is distinguished by its specific properties, and the selection logic is initialized once per a specific type of operation, regardless of the message size, and then it can be reused across all the messages of the same kind of operation. In addition, since all of the initialization is separated, we have an easy protocol restart if endpoint configuration is changed. What does this mean that endpoint configuration is changed? It means that the set of transport, the set of remote addresses, or any one of those has been changed for a specific UCP endpoint. It can happen today as part of a client-server wire process, For example, we can start with one connection manager lane before we have any kind of idea what the remote side has. We have some internal protocol, and after that, we initialize the actual transports. And we can do it in two phases if the address is too big. And the user can be already queuing some requests on the endpoints. And if we started to send those requests, we may have to start them all over again. And it can be done very independently and easily with new protocols. We also have future plans to allow changing transports on a specific UCP endpoint during runtime, even after some protocol is already started and sent some data. And this can already be done by the same infrastructure. And so probably many people here are already familiar with that, but just to recap, the major building blocks in the code of new protocols. So the proto-T structure defines the major callbacks, like the protocol progress function, initialization function, and abort and reset. Select param structure is a set of parameters that affect the protocol selection. It's we can call it a tuple of data type, memory type, system device, operation type, flags, and so on. The protocol init parameters is some common building block that is used throughout the protocol initialization flow. It contains common parameters, how the protocol can be initialized. And we also have protocols which extend other protocols. For example, rendezvous protocols extend the basic protocols, and there is also some hierarchy within the rendezvous protocols. Also, the init parameters is extended the same way. The protocapsT is a structure that is the output of protocol initialization. Actually, we go through each protocol, and the protocol is being initialized. If it's successful, which means the protocol can really operate and accomplish sending a message of a specific type, it will return a field protocap structure. And this structure is specifying the performance estimation for every message size range that is supported by the protocol. And we also have a few families of APIs and structures. Proto single stuff is handling all the things that are related to protocols that send only one single message. This is kind of optimization for small message protocols like short or bcopy single or zcopy single. We can skip many of the checks and just send one message. Proto-multi is a very generic infrastructure that can handle fragmentation, multiple messages, multiple lanes. It can balance the bandwidth between the lanes according to their estimated performance and topology and so on. Many of the large bulk transfer protocols, such as rendezvous transfer, are derived from proto-multi. And proto-select stuff for all the functions and structures that are actually making up the common selection logic. It includes driving the protocol initialization, analyzing the ranges, applying a user configuration, and eventually selecting and building the structures that designate a specific protocol for every supported message size range. So how we handle rendezvous in protocol v2 is deserving actually a special slide because it's a bit tricky. So usually if we have a simple protocol like eager that is only sending something to the remote side, we can just estimate how long it would take, let's say, to copy the message or register the memory and send the data using the selected transport or lanes and so on, and that's it. That's enough to estimate the performance. However, with rendezvous, it's a multi-step protocol. We depend not only what the local side is doing, but also on what the remote side is going to do. So the process is kind of similar to min-max algorithm, where we start with a rendezvous protocol that is sending a RTS message, because RTS is always the first phase of doing a rendezvous protocol. And then we try to estimate what the remote side is going to do with our buffer. And we do that by creating emulated selection parameters that is going to be how the remote side views the parameters that we sent in the RTS message, which means the pointer, a remote key, and any additional information that we have. And then we assume the remote side will do the best thing. And then in addition to the time that it takes for the remote side to complete the operation, we add the time it takes to send the control message itself, meaning the RTS message. And then we get the overall performance estimation for rendezvous. But also, when the remote side is going to estimate the performance of fetching the data from the sender, it may be not as simple as just reading the data. Maybe the remote side will also decide to respond by a control message that is called the rendezvous RTR. And then there is another extra step of doing the inverse side of estimating performance. And the receiver side is actually estimating what the sender is going to do with the RTR. And then on top of that, adding RTR overhead. And then in turn, the sender adds RTS overhead. And then taking all of that into account, we get the overall performance of the whole rendezvous protocol exchange. And on every step, each side will select the best option that it has. And after, during runtime, actually, all what I mentioned above is happening when things are initialized. But at runtime, when some process would receive a RTS or RTR message, all the selection process can happen all over again. But if we already have some cache information on the worker for the same configuration and buffer type and selection parameters and so on, we can reuse it. Pipeline protocols actually have another extra level of selection. Rendezvous pipeline is just a template that breaks apart a large request into smaller fragments and tries to select a protocol that would execute each one of those fragments. It's similar conceptually to rendezvous in the sense that we're trying to select an underlying protocol. It's just that it happens on the same side and not on the other side. And eventually, after we get the best performance estimation for rendezvous, which is actually for rendezvous RTS, then we compare it to the other candidates that we have, such as eager bcopy or eager zcopy. And this would decide, so to speak, the threshold between eager and rendezvous. Okay, so let's take a look of what we did in the last year. So we implemented all active message variants with new protocols v2. We added optimal alignment to the existing rendezvous protocol. We had it in protocol v1. It's actually important that when we write to the PCI, that the writes would be aligned to PCI MTU, so it would be optimal. Also, we moved the memory registration cache to UCP layer, added the error handling flows. We added the performance tree and protocol select information to trace the selection process. We had a few improvements in the PCI topology detection. We added support to have more lanes for UCP endpoints to enable GPU aware selection. And we're currently reviewing a GPU memory two-stage pipeline that enables optimal data transfer between two GPUs on the same system if CUDA IPC is not available. And we'll have details on all of that during this presentation. So preliminary plans for next year. So mostly we want to do performance tuning and tracing the protocol selection and make sure that we're always doing the right thing. Specifically, we already identified some issues with blocking unblocking send threshold, and currently there's a pull request and review to fix that. We also noticed that sometimes, even though we have multiple lanes available, it's not always beneficial to send on all of them, especially for small or medium messages that could depend on the message size. So we have some threshold for rendezvous, but we want to make it more generic and use the overhead of send operation to select the optimal number of lanes. And in general, our goal is to to have a more accurate performance estimation for each protocol independently, and that would eventually give us the best thresholds between the protocols. So as part of that, we want to enable the protocol v2 by default. Currently, we can turn it on by setting UCX proto enable is equal yes, and then gradually we can remove a protocol v1 code and do some code cleanup. Also, we're going to work on a zero copy rendezvous with IOV data type. Currently, if you would pass a IOV data type, it would either use a eager protocol or a rendezvous based on an active message. Both of them are not efficient. Also, we want to do some optimization with regards to memory registration. So we can register memory region only after it was used a few times, and that is made easier because we moved the registration cache to UCP layer. So we can track all the usage from the protocol before we try to register it. Also, we had some issues that we want to fix by knowing how to recover from a memory registration failure. Those could happen because, for example, we run out of resources on the memory domain, or maybe in case of GPU memory, a GPU with small bar, or we run out of some resources on the NIC. And we don't want to fail in this case. Today we fail, but we want to fall back to vcopy protocols. And we also have plans for GPU memory pipeline, though we planned it for this year, but looks like it's been postponed for now. Okay, so for the next parts, kind of having a deep dive into each of the things that we did this year, feel free to ask questions. So active messages, we added multiple protocols. So we separated the reply protocols and the protocols without reply. This gives some optimization and reduces runtime branches, because after a protocol is selected according to the flags, we don't need to check anything anymore. We already know what to do, and the progress functions is built with everything decided at compile time. So we have eager short protocols, bcopy and zcopy single, and bcopy and zcopy multi. Also, we're porting the support of a new flag that we introduced, copy header. This flag is a reminder, allows users to pass an active message header that is being copied into an internal buffer in case the operation cannot be completed in place. So this is in review now. So also it's as part of several optimizations, we moved the registration cache to UCP. It's going to replace the registration caches that we have in UCT layer. They still exist today because we use them for Proto v1, and we don't want to just degrade the performance of Protocol v1 by removing them. We have a pull request in review to also move protocols v1 to the UCP registration cache. So moving that allows us to lower the zero copy overhead, because we don't need to take any logs on the registration cache. We can rely on the UCP context log. In case of a single threaded MPI, we don't need to take any log, and we know that we can know that. Also, we can inline all the functions into UCP layer and significantly reduce the registration cache lookup overhead. And the original motivation for that was also to support DMA buff in a better way, and to query DMA buff file descriptor only if we actually miss the registration cache lookup, and not every time. And as mentioned before, it allows additional optimizations like tracking memory region usage, and register only regions that are used frequently, and if they are used infrequently, we can just fall back to using vcopy. Regarding the error flows, so each protocol defines abort and reset callbacks. with protocol V1, we just had a single function that handled all protocols. It's kind of a mess, but here we can really separate and do the right thing for every protocol. So abort function would complete the send request with error, and when there is some kind of network error or some kind of, or one of the UCT operations as part of the protocol execution failed. Reset, on the other hand, the goal is to bring the send request back to its initial state that happened before we just started to progress it. And we can do that in order to clean up existing protocol and select a new protocol and continue with the new protocol. Also, we have a few things currently in progress with regards to error flows. So we also want to implement the support that we had in protocol V1 to invalidate remote memory keys as part of a rendezvous protocol aborts. And we also have planned to increase the CI coverage. So we have some kind of random or a semi-random set of operations, error injection, and make sure that everything is cleaned up properly. And so we also added a way to show which things are being selected at runtime. This kind of information is intended mostly for users or advanced users. So just by adding the flag UCX proto info equals yes, obviously assuming protocols is enabled, we can see which kind of operation at high level is going to be used for every message size. So there are multiple configurations. So here we can see that internode MPI, MPI comes from PML UCX in OpenMPI, and internode also comes from that. And it's an endpoint configuration for communicating with other nodes in the fabric, contrary to a cell for an intranode. The operation is a rendezvous data fetch, which means it's how the receiver would respond to a RTS message that is going to read into a CUDA memory, device memory, also from CUDA memory. So we have that because we run OSU bandwidth with device-to-device memory. So we can see that for 0 byte, it's just an empty operation. For 1 to 64, we use a RDMA write. That's because the minimal size for get-z copy on this configuration is 65. And then starting from 65 to 16K, we use a 0 copy read. And for larger sizes, we use a pipeline. So for up to the fragment size, we just use a single fragment protocol. And for sizes that are larger than single fragment, we pipeline all the fragments. So why does that happen? On this particular machine, there is no PCI switch, and the bandwidth between the GPU and the NIC is quite limited. It's about 3 gigabytes per second. So, but also from the other hand, there is some overhead of CUDA copy for the pipeline protocol. So it turns out that, according to this selection logic, that for relatively small messages, it's better to have a lower bandwidth, lower upper bandwidth, instead of paying the overhead of CUDA memory copy. At least that's how this selection logic is currently tuned. And there is another way, and I'm going to deep dive into it, is the proto info tree. So we can, if we set the environment variable UCX proto info dir to some path, then we'll get a bunch of dot files that describe a graph of how the protocols are being selected top to bottom, including all the performance numbers. And eventually, by going over this graph, we can answer the question, why is, for example, rendezvous is used and not eager. And by tracing all the selection steps, we can identify potential issues and improve the selection process if needed. So I'm going to share another window So as you can see, this is a visualization of the graph. And the way that we can work with it is by like similar to looking at a map. So we start with the root and we see that the operation is a rendezvous pipeline, a CUDA copy, and this is what is being selected. And the next selection step is to select the best multiple fragment protocol. And the options that we have is either using a rendezvous protocol, or we have a multi-Z copy protocol or multi-B copy. The meaning of pipeline is that we send multiple fragments of multi-B copy in pipeline with one another. Here we can see that the selected path is a rendezvous, and we can see the performance estimation for rendezvous. The performance estimation here is about 8,000 megabytes per second. Unlike the eager, that is about eager Z copy is about 3,000 megabytes per second, and the eager B copy is even worse than that. So next, we want to see what the rendezvous protocol is actually doing. So stage means that we do things in parallel. So we do memory registration, we pack a remote key, we send the RTS control message, and the performance of RTS control message is coming from the transport eventually on how long it takes to send one active message be copy. And then we add and extend a few things on top of that, and we get the RTS performance. But the major part of a rendezvous is what the remote system is doing. So what is it doing? It's also staging a few things. It has some overhead of protocol selection, it has to unpack the remote key, and then it has to accomplish RDMA receive operation. And what is the RDMA receive operation? This in turn is selecting the best of a few options. We can either do a rendezvous get Z copy, just read the data from remote side. We can respond by sending a single RTR message, or we can do something in pipeline. And the selected path is do things in pipeline. So we cannot use CUDA copy with single RTR because the message size is too big. So we must use a pipeline in this case. So what the pipeline is doing, the pipeline also has two options. It can either send RTR message to the remote side, to the sender side, and ask the sender side to respond with RDMA write, or it can use a RDMA read pipeline. And in this case, we selected the put pipeline because the RDMA read pipeline is actually not that optimal because the remote side is still going to suffer from the poor bandwidth between NIC and GPU. That's why the multi-bandwidth is actually limited by something that is estimated as 3.5 gigabytes per second. This is actually the PCI distance between the NIC and GPU. So then in turn, we estimate the performance of rendezvous RTR M-type. M-type protocol is something that is capable of sending RTR message. And after the remote side did the RDMA write to an allocated temporary fragment, which is also called the MDESC in the code, this protocol would copy the data from the fragment to the actual user buffer. So what is it doing is it has to pack the remote key into the RTR, actually send the RTR. Then the remote system is doing its thing and writing the data. After it's done, we have to copy the memory from, let's say, host to GPU. This is also taken into account. And then in turn, the remote system is actually the sender side now has to unpack the remote key from RTR, and then it has to send the rendezvous data. And long story short, it also estimates the performance of rendezvous pool that is staging transfer, overhead, and copy the data from CUDA to hosts, as written here. So what we expect of the optimization process is actually running benchmarks, understanding if the reason for performance degradation is because we selected the wrong protocol, and then go over the selection tree and understand which performance was not estimated correctly. Okay. So let me go back to the slides now. Yeah. Okay, so near the bottom of the slides, we have a link to this GIST that I showed before. Okay, so in order to really to estimate correctly, we had to make a better estimations on the topology distance between NIC and GPUs. So currently, the topology code distinguishes between two kinds of distances. Either it's inter-socket, which is called also system root, or it's two devices that sit on the same root complex. In this case, the bandwidth is inverse proportional to the amount of different path components, which is some approximations of the distance between the devices. In the future, we want to also maybe add this system-specific bandwidths or numbers. Probably different kinds of servers have different bandwidths, but this is close enough for now. Also added the topology information to UCX info tool. If you run a UCX info -t, you get all the system devices in a table that shows the bandwidth between them. Inf means that it's infinite bandwidth. It's like the maximum you can get, and it means that the PCI is not going to be a limiter for this communication. For example, MLX50 and GPU 1 and 0, they sit on the same PCIe switch, so their distance is considered infinite. Okay, and as for the number of lanes, so until recently, a single UCP endpoint was limited to about 6 lanes. The lanes were representations of devices and transport that are used for the endpoint. They can use potentially for different protocols, not necessarily all protocols are going to use all the lanes. But with systems that have multiple NICs, we ran into an issue that we can select the best NIC only if we know the GPU upfront, because we cannot create a lane for every NIC in the system. But now that we have enough lanes in the endpoint, we can actually create a lane for every NIC in the system. But the protocol, for example, on the VUR protocol that is derived from a proto-multi, can take the GPU pointer. It already knows the system device of the GPU pointer as part of the memory detection. And then it can select only the best lanes, the best NICs to use for this specific pointer. This way, we don't need to select the GPU up front, and we can also use multiple GPUs in the same program and still select the best NIC to use. So already merged the code to support up to 8 lanes, and up to 16 lanes is currently in review. It's a little bit different because we had to extend some of the bit maps to 16 bits instead of 8. Also, the lanes, the extra lanes are represented as slow path lanes as part of endpoint extension. So we wouldn't allocate memory for them unless they are actually used. Okay, so actually I'm done. Quite ahead of time. Does anybody have any questions?
So reminder to people attending, all of you muted. So the only way to ask questions, I believe, is to post in the chat or in Q&A. And to give you a couple of minutes to prepare your questions, I have a long list of questions, Yossi, for you.
Okay.
Not very long, just 4. You mentioned in one of the slides that GPU pipeline is not supported in V2. Is this kind of degradation from previous V1? Because I know you have three-stage pipeline protocol in V1?
Yeah, so for protocols, we actually have to implement each protocol in addition to what we had in Proto V1. So currently, protocols V2 do not support the two-stage pipeline. I guess that's what you're asking about, the intranode one.
Two and three-stage. I'm asking about both.
Okay, so three-stage is already supported for quite a while.
Okay.
And we can see it's being selected in the graph I showed before. The two-stage is currently in review. It's for an intranode.
Okay. So, but it's not supported for now, but this is something in V2 will be supported, right?
Yes.
Okay. And this is a patch in review, right?
Yes.
Now, you made a comment that if for whatever reason you fail to register GPU memory or bar is too small, you want to transparently switch to pipeline protocol. So
well, not necessarily pipeline, but the next best choice that does not require registration.
So there is kind of feedback from users that we hear that sometimes it's actually preferable to return an error over automatically degrading performance. Return some information because there's two possible options. Some user may decide, okay, I will go and, let's say, fix the bar size in a system. This is one option. Another option is upper layer may decide to implement own optimization on top of this and work around this problem.
Yeah, that's actually also had a request similar to that. We had some ideas to add another flag to the request, something like a force zcopy that would make sure that either only zcopy protocols are being used or the operation would fail.
Yeah, it can be per request. I almost think it's more of global sync. If you like, at least use cases I hear now, it's almost like context level, if you ask me, where, like, generally speaking, they just want to know about these problems and deal internally in upper layers with this.
So I'm not sure it would be okay to have it per context, because you can have multiple types of operations, maybe even control messages or host memory or small messages. Not necessarily want to force zero copy on that, unless you kind of configure some kind of message size threshold.
Well, it's why it's interesting problem to solve, but I think it's request level, it's possible, but it might be too fine-grained. It's kind of separate discussion we can have, don't have to solve all of this now. In your slide where you showed protocol table that you generated for, I think, Open MPI, it explicitly states MPI threshold sizes and so on, MPI internode. So is this MPI generated or UCF generated, or why it's MPI?
So this is a patch that didn't have stream yet. The MPI string is MPI generated because it's coming from a UCP context create eventually. Like you create a context for MPI, and the internode part, it's an API that I wanted to add to a UCP endpoint create. That whenever you create an endpoint, you can specify which kind of endpoint is it. Another option is somehow detect it in UCP, in UCF internally. For example, if you have some reachable shared memory transport or something like that. But I think that could be a problem because sometimes you would restrict your transport, let's say, only to IB, even if you're running on the same node. And then the information could be a bit misleading, unless we pass some debug info in addition, like the host name or something like that. Pasha, I don't hear you.
Sorry, I have one more question. I was on mute. And in the current topology report that you showed in one of the following slides, I believe, it's super helpful, by the way, but a bit of sort of criticism, not really criticism, but like something to improve. If you get similar report from NVIDIA SMI tool, it is much more detailed.
It's
in
kind of
terms of
similar to
discovery.
SMI. Maybe we miss here more information that you have in SMI, like more details on the GPUs, because this is just topology.
Mhm.
You have additional flags to UCX info that are not minus T that show additional information about UCX.
Well, in NVIDIA semi-topo, you get information about if it jumps through the switch, if it directly connected to root complex. It's more detailed, or in VLink, it's more detailed about hierarchies that it discovers. So it would be useful if kind of you can add hierarchy information to the numbers as well.
Yeah, you mean in addition to knowing the bandwidth and the latency,
Yeah.
let's say, that is needed for protocol selection, we also need some kind of variables or title or some kind of.
They have acronyms like PBX and other ones. They have a couple claiming.
You want to know why the bandwidth is like that.
Exactly. Like why is the number that is reported, why it is number. For example, infinity, like we chatted at offline, it's kind of confusing because it's not really infinity. It is limited by PCA root complex, right? Like it's or PCA switch, you recite as the same.
Yeah, I guess we can think of a better way to make it more user-friendly view.
Yeah, because again, sometimes number and topology, like, oh, hey, I don't want actually it goes through other PCA switch. Essentially will provide, because today, what I personally use a dump of this information combined with NVIDIA's SMI tool to kind of get the full picture.
Yeah.
I don't think I have any other pending questions. We have one comment posted in a Slack question. Do we have access to the slides in GitHub for the new features? Question from Jacob. I can answer probably this. So all the features in code and everything in pending features, whatever was published, it's available on GitHub. We operate open source by default. So all the stuff is show ups on GitHub, and most likely whatever Yossi showed already, all of this in pending pages that under review. And slides, we will be gathering slides from presenters, and we will be posting online on GitHub. As well, we will be posting video recordings. Yossi, do you have any comments on the features part of the question? I think all you presented, it's
So all the
summary.
features that's presented in the first slides, except when stated explicitly, are already mirrored. And there's a bunch of other features that are currently in review.
Well, in review, which means it also on GitHub in pending pull requests.
Yes.
Any more questions? Let's give a minute to people to think about questions. Okay, we have one more question, COC. Is there an estimate timeline for when V2 will completely replace the V1 protocols?
So we kind of currently estimated during the first half of next year. We still have a V1 around for a fallback, but we plan to make V2 the default during the first half of next year.
Thank you for the question, and thank you for the answer, Yossi. Any more questions? I don't think we have any additional pending questions. Yes, you finished a little bit earlier. And let me share the schedule. So you should be able to see my browser. So we just finished protocol V2 update by Yossi. Yossi, thank you very much for presenting this. Really exciting. I think the graph rendering of the protocols looks really cool and really useful to figure out what's going on inside of the library. We have break until pretty much from now, because we finished earlier, until 11:00 Pacific time. And after the break, we'll come back for a next series of talks. We have 2 talks queued up. After 11 Pacific time is UCF exported memory key API for better DPU experience by Dmitry Gladkov from NVIDIA, and UCX multi-rail support for MA by Sergey. So please, which means roughly speaking, we have another, how much time we have? I'm trying to translate it from Central Time to Pacific
Hour
time.
and 15 break.
Yeah, 1 hour and 15 minutes break. And yeah, please reconnect or stay online till the next talks.
All right. Thank you, everyone. We'll see you back at 11 a.m. Pacific. All right, everyone. It's just after 11 o'clock. Hope you enjoyed your break. Pasha, you here? You want to introduce the next speaker?
I'm just was too busy with responding on emails.
Ah, yes.
Let's make sure that we have our next speaker online.
Yes, I'm here.
Dmitry. Okay. Hi, Dmitry.
Hi.
Do you want to go ahead and try it and share your slides?
Yes, I will do it.
And as you share your slides, let me introduce Dmitry Gladkov. Well, since Dmitry did not share his bio, the introduction is going to be relatively short. Dmitry Gladkov is coming from NVIDIA. I believe Dmitry is one of the active members of UCX community. And in his talk, he will be talking about UCX exported memory key API for better DPU experience. For those that are not aware, there's new very cool feature coming into UCX that will let DPU directly access the host memory and execute operations on behalf of the host without need of going through bouncing buffers. And I believe in this talk, this is the subject that Dmitry will be covering.
Sure.
You may want to go into shared mode so we can see you.
Yeah. Oh, okay. Can you see it in shared mode or?
No, we
Looks
see your
looks I
slides.
know. Yes, sorry.
You have to go to the bottom right. There is this like small icon of presenter mode next to the zoom slider. Yeah, user go down. So there's one of these icons where it's like looks like monitor, it's presenter mode.
Yeah. Oh, by some reason it's okay. Let me share it another way.
And if you're in multi-monitor setup, it's
Yeah.
you have all kind of different challenges.
Yes, looks like so.
As for the audience on the call, again, guys, please ask questions in the chat and Q&A sessions. Questions more than welcome, and hopefully after the talk we'll have fruitful discussion.
Okay, looks like some problem with sharing in multi-screen mode. Okay, let me show like it currently have. Okay, so let's get started with my talk regarding new UCX exported memory key API.
Hey, Dmitry, it's still in this not presenter mode, essentially. We can see like your slides and sort of regular.
Mhm.
What happens when you go to view?
Yes, it shares to
slideshow?
my another screen. Let me. Sorry,
Okay.
yeah, can you see it now?
Yeah, it is perfect.
No.
Thank you for fixing this.
Yeah, sorry for not being prepared. Okay, so as I told before, here I would like to present a new API to enable DPU devices and for offloaded applications using UCX API. This API could be used currently with NVIDIA DPU. And let's talk about what is DPU. DPU is data processing unit. Actually, it is a system on a chip which can combine three different things: high performance network interface, multi-core ARM-based CPU, which can help applications to run some offloaded operations by just writing some daemons and running them there, and flexible and programmable acceleration engine, which can also offload some network functions on DPU. So how DPU could be used with previous version of UCX, with current one, which actually it's pretty easy how it could be used. There are two types of applications, one running on the host. For example, it could be some collective framework. On DPU, we have another type of application which offload some work from host. We can call it daemon. And data should be sent from processes running on host to processes running on DPU. So DPU should have some buffers allocated to receive this memory, and then after doing some work, receiving some data on GPU, we should send this data back to host. So actually there are many problems with this approach. The first one is, like we see, memory usage is increased because we need to allocate memory on DPU side also, and have a copy of users buffer there. And SoC memory size is limited, so we can reach full memory, and it will lead to out of memory problems. So we should be aware that we not reach this. And also another problem, performing send receive operations between host and GPU, which uses network, and can lead to problems with other connections which are performing data transfer using the same network device. In new version, in upcoming UCX version, this approach could be rewritten in currently implemented applications by using new API. Now DPU can access memory allocated on the host directly without any data transfers from host to DPU. So we can directly do send receive of active messages, tag matching, rendezvous operations, RMA, atomic operations, without involving host CPU into this process. So what we will have after implementing this approach, memory usage will be decreased in compared to the previous solution, and host and DPU will exchange only small packets to specify where the memory is placed, and sending some L key, which could be used by DPU, by processes running on DPU to perform operations there. So how it could be used by applications? So in UCX, we introduced new APIs on UCT and UCP layers, which expose cross-GMI capability of NVIDIA Bluefield GPUs, which this API provides easy DPU adoption for RDMA applications or collective frameworks like UCC, and this API has some abstraction which could be used by other DPUs, by DPUs implemented by other vendors. So it is not only limited by NVIDIA devices. So let's switch to UCT API, what we have there. Actually, before starting use and register and use memory, we should query devices and transports whether they support exported memory key feature or not. So it could be done by new interface UCT MD query v2, which will say in flags whether exported MKey supported or not. After that, we can perform work related to this API. If it is not supported, actually, application can fall back to offloaded mode without using exported memory key feature. So how it could be used if this feature is supported? On the host side, we should register memory key with export flag by using memory v2. It will allocate memory handle, which could be exported to processes on DPU side. Then process which is running on host side should pack this exported memory key to pre-allocated MKey buffer. The size of this MKey buffer could be took from MDAtor attributes also. We have new attribute called exported MKey, exported packed MKey size. And then this MKey buffer should be sent to process running on DPU somehow. It could be also done by means of UCT API or some other mechanism like socket interface, etc. And on DPU side, we should attach local memory key to the exported memory key received from host side. It should be done by means of UCT MD mem attach API function, and we will get new memory handle, which could be used then for active message or my atomic operations. In UCP API, it's pretty aligned with the UCT API. On the host side, we should register memory handle with export flag using UCT memmap API. If UCP memmap API returns error unsupported, it means that exported memory handle cannot be used in the current setup. So it means that there is no devices which support this feature. So user can fall back to another offloaded mode. Second part is packing exported memory handle using also new API, UCP memh pack. Here, memory for memory handle buffer will be allocated by UCP, and the size of this buffer will be also specified, will be stored in last parameter. So this buffer should be somehow sent to the DPU side, to the processes running on DPU side. And only after that, this buffer could be released. Actually, here, third and fourth items should be not in correct order. Okay, on DPU side, after receiving memory handle buffer, we could start registration, but before that, we should make sure somehow that this feature could be used by transports selected for active message, tag matching, RMA, or other protocols, to make sure that we should specify new feature flag for UCP init. The name of this flag UCP feature exported memory handle. And if there are such devices, UCP init will return UCS OK as usual. And then when we receive packed exported memory handle buffer, we could start importing and creating local memory handle. It could be done also by means of UCP memmap. We also specify export flag, and also we need to specify received exported memory handle buffer through parameters. So the result of this operation will return a memory handle, which could be then used for active message, tag matching, RMA operations. But I need to mention that all operations will use rendezvous inside it, because eager operations can be used because we need direct access to memory without copying it somehow to some staging buffers on DPU. So that's why a rendezvous protocol will be used inside. Now let's discuss a bit how it was implemented in UCP and shed some light on some major changes. Actually, we introduced a new memory handle packed buffer, which could be extended in the future via compatible with previous UCX versions. And here you could see how it looks like for exported UCP memory handle buffer. And this memory handle pack buffer also will be reused for RKey buffers. So it will be packing could be done by the same API and will be extendable for future needs. Now, when this packed memory handle buffer received on a TPU side, we need somehow match MD map, memory domain map from host to the local one, because configurations could be different, because on a host we can have not only Bluefield device but also some other devices. So memory domain indices are not don't have direct mapping, so we pack some special MD attributes, which are also introduced during introduced in UCT API. It is component name and global ID. Component name is actually TCP, IB, or etc. And global ID in case of NVIDIA devices is or other IB device could be GUID. And to resolve local MD map, we doing comparison between component names and global identifiers. And by this process, we generate MD map of local MD map. Since memory registration of exported memory handle and memory registration of imported memory handle could be very expensive operation, we should cache it somehow. I mean cache the result of such operations, memory regions, memory handles. So in UCP, we already have rcache, which I guess in the future will fully replace rcache from which is currently we have on UCT layer also. So for caching exported memory handles, we could use existing rcache in UCP, but we also need to cache imported memory handles, and in this case, using existing rcache is impossible. So because we have different on DPU side, we have different processes which are going to share with us memory buffers, and their virtual addresses of their buffers could be intersected. So we introduced hash over caches in UCP layer. Hash key is UCP context UID. It is a unique identifier of UCP context on which memory was exported, and the value which we can get from hash is a rcache for a given peer, and after that we should do lookup in this rcache to find a region or create a new one if region wasn't found. So regarding results, to evaluate this work, we implemented a small benchmark. Actually, it is non-blocking Algorithm collective with some additional work done during executing collective. We actually do some computations. It is matrix multiplications, and we measured. We implemented two schemes. First one, just a float without using exported memory handle. It is sending data from host to DPU, and then DPU performs send operations to another DPU, and then DPU, receiver of this memory, performs send to receiver of this element. And also another scheme using exported memory handle without requirement to send data from host to DPU. DPU in this scheme, DPU can directly access the memory from host and send or receive directly to host memory of target site. So you can see in this slide how bandwidth was increased using offloaded mode with cross-Gavami capability, and overlap as expected is very high in both schemes. So what's the current state? Currently we have two open PRs in GitHub, in UCX GitHub. It is the first one implementing UCP API in a perf test. Also, we have UCT implementation. Currently, it is under review. So API both for UCT and UCP have already been merged to the master branch, and also UCP implementation will be upstreams very soon. And for whom is going to try this feature of UCX, I posted a link to the entire implementation. It is currently in my GitHub fork, but you can try it. Also, how to test it. In UCX, we introduced usage of this API in our UCX perf test, but it's currently not merged to any releases or to master branch. So some options and etc. could be changed. Actually, it's pretty easy to test. It is normal UCX perf test with all parameters you maybe already know, but currently it is supported only for UCP active message API. What you need to specify, it is only perf daemons addresses and ports if you're not using the default one, and run DPU on DPU perf daemon, which accept connection from UCX perf test and offload active message operations. So that's all. Maybe someone have any questions to me?
I do believe there is, I see at least one question posted in the chat. Can this API also be used for the reverse scenario? Host-initiated network operation can access DPU memory.
Good question, actually. We tried, be honest, we didn't try this scenario, but we tried accessing host memory from another process which is running on a host memory. So doing export on a host memory and then importing it. It doesn't work in the current firmware version, but I do believe that it doesn't work because firmware returns error code, which means that we can't use alias memory key on the same Gavami. So since we will do reverse scenario, I mean exporting memory on DPU and accessing on a host, we'll use different Gavami. So I think it should work, but I guess it will be easy to test using perf test. So I can try it and can post the result here in the chat.
Thank you, Dimitri.
Thank you too.
Any more questions from people online? We have one in Q&A. Let me figure this out. Can GPU memory be exported too?
There is no limitation. So yes, it could be used, but currently we didn't test it, but it should not be a problem.
Okay. Let's mark it as answered. Any more questions from people online? So I have one question, Dmitry. Very cool feature. What is the timeline, do you think, to get this into upstream and release?
API is already merged to the main line. So currently we are upstreaming implementation in UCT IB transports. So we already have opened pull request. It's currently under review, and next step is open pull request for UCP, which could be reviewed in parallel with UCT implementation. So I do believe that it should be part of U6 1.14. So don't see any limit to do it.
Okay, thank you. I don't believe we have any additional questions online. Okay, we are back for the next presentation. Sergey, here? Okay, let me do just brief introduction. Our next presenter is Sergey Oblomov from NVIDIA. He is one of the UCX community members and active developers of UCX library. And in this talk, he will present UCX multi-rail support for remote memory access operations.
Okay, thanks, Pasha. Hi there. Originally, it was going to be the short demo, but after we got agenda, it became clear that we should just create a few slides to describe what are we doing here. Okay, I'm going to briefly discuss what is the multi-rail itself and what kind of the UCX, describe how multi-rail works inside, and describe some limitations and make demo itself. I'm going to be short. Sorry, here is late. Okay, let's start. Oops. So let's say that you have a computer where multiple HTAs, if you have InfiniBand or NICs, if you prefer Ethernet, or maybe some combinations of these devices, or multiple ports with such devices are attached to your computer. And you have an idea to use it as a single, very, very powerful network interface or network logical device. Yeah. And the idea comes to many people who works with HPC. And such logical object is calling multi-rail. This logical interface should make three top features. It should share network resources between physical devices like a bandwidth, maybe directions. I've seen the articles where describes the combinations of such models and a lot of exotic things. And it should provide resource balancing between devices. It's especially actual for schemes where you have devices with different performance characteristics. For example, different generations of Mellanox devices where performance may be different on times. Yeah. And the most critical thing is provide synchronization between such devices, because previous two items, if you will not provide it stable working, yeah, you will just have the performance degradations. But if you does not provide valid synchronization between devices, for example, valid ordering, you will break the data integrity and it may fail some calculations. Yeah. UCX model. In UCX, we are using model is the most straightforward. It's just share bandwidth between devices which is used in multi-rail. It means that when you send, for example, a big message, it just split this message across all devices and trying to decrease time for sending such message to, yeah. And multi-rail for send receive operations. UCX was introduced in UCX about 2 years ago, approximately. And the multi-rail for RMI operations, it's in progress. We are going to get it in next release, I mean 1.14, and it's on the way. Okay. Okay, now let's look at the how multi-rail works in UCX and what the limitations and possible issues we got and going to resolve. So, what is the difference, conceptual difference between single rail and multi-rails? Yeah, if you look at the left side of the screen, yeah, we will see that any send operation, send or RMI operations consists of several steps or several phases. First one is we have to map user-defined memory to the adapter. I'm talking about IP specific. For TCP, it's quite similar, but there are different steps, but the common term is the same. So we have to, next step is we have to post operation, put some frame into the NIC adapter, yeah? And after this, adapter will use this data to transfer message to peer. And it's a common scheme for any physical adapter. But with multi-rail, if you look at the right side, we will have some kind of the duplication, but with some time shift. Yeah, because when we're starting operations with on first lane, yeah, for example, we're starting memory map, post operation. After this, NIC is starting transfer data. Only after we make things, for example, memory map on first lane. Only after this, we can start memory mapping on the second lane, because we are operating in context of the single thread. Multi-thread is not used for now. And we have to make such steps, step by step in single thread. Yeah. And that's why we have some kind of the issue here, like how to provide synchronization of completions. It's a problem because, as you can see, our rails may be imbalanced for some reasons. Hardware performance, maybe network issues, something else. And we have to provide synchronization on the multi-rail level, on the level up. It's one of the issues. And this leads some more issues. If you look at the pipeline again, we may see that we have two global stages. First one is overhead for any operations. It's not a data transfer itself, but it's some period of preparation data to be ready to be transferred to wires, to peer. Yeah, and if you look at this more detailed, we may see that overhead does not depend from example from message size. Such operations technically it may correlate with message size, but in common picture it has just constant time. Yeah, and it does not correlate with message size. In some cases, such overhead, some steps may be comparable by time with data transfer itself, and it leads us to conclusion that multi-rail is most effective on the big data sizes. Yeah, and for zero copy protocols, because big copy have some additional limitations which break us to make good balance between overhead and data transfer. And the worst situation here is that the timing limit, like message size divided by rails, this formula could not be reached in ideal, yeah, because you always have overhead, and even you split your message on the multiple many rails, physical rails, you'll have constant overhead, and this overhead will add some disbalance, yeah, and it does not allow us to have a message size divided by a number of rails time decrease. Okay, and of feedback. Okay, so now let's look at the demo. We are using OpenMPI version 1.4.1 UCX master branch, using hardware 2 Mellanox connected 6 adapters per host. Benchmark is OSU. Put memory rate over the heap. Transport RCX and 1 and 2 levels or lanes. Okay, let me switch to my console. So, Pasha, can you see console window, terminal window?
Yes, I can.
Oh, okay. So, on the left pane is, oops. No, please. Zoom is really strange application. Okay, on the left pane, we are going to run singular application, and on the second pane, on the right pane, we'll use 2 lanes. Okay, and let's look at the result difference. Okay, first one and second one. One more. There is difference only on number of rails. Absolutely, all the things is absolutely the same. And if you look at, for example, the message sizes starting from megabyte, we will see that on the single rate, the message rate starting with 12, 1 to 195. And on the 2 rails, it's about 19,470 messages per second. You see the difference? It's not 2x, but it's a significant difference. Are you agree? So actually, that's all what I was going to show you today, because one more, it was going to be demonstration of our progress. And it's a good demonstration of overhead and useful job. My previous demonstration of slides, it was overhead, and useful job is just running these benchmarks results. That's all. Questions?
You have a substantial performance drop when you go back to your.
Yeah. We have some issues with selection for protocols. We are
4K,
used
4K you have like
4K,
insane.
2K, and
No, 2K is fine. 4K it's where it goes really bad.
Yeah, because here is used as new protocols, as you remember, demonstration from slides from Yossi, and it's not perfect for now, and we have a gaps with protocols selected for particular message sizes.
And how performance will change if you have NICs of different capacity or different locality of the NICs. For example, one attached directly, another one attached through PCIe switch or something. Can you identify this performance?
So with protocols version 1, we just identify the difference between the NICs themselves. But with protocols v2, we also take into account the PCI topology. So we calculate the total bandwidth, which is actually the maximum, the minimal bandwidth between a PCI topology and the NIC itself. And that lane would receive a proportional amount of data relative to the actual bandwidth. And if the bandwidth of the NIC, including topology, is too low, I think it's like 4 times lower than the maximal, then we wouldn't use this lane at all.
Makes sense. Yeah, I remember, like, even for GPU, I think you have similar selection logic if it's like 4 something. Is it for some magic number or?
It's a configuration, but I guess going forward, I mentioned that we want to somehow select the number of lanes also based on message size and performance. So maybe it would be more dynamic. Also take into account the actual overhead of posting something into the lane.
Makes sense. So let's see if you have any pending questions from people online. I don't see any pending questions online. Okay, let's look at the schedule.
There is next break.
Okay, next to break. Well, Sergey, since we don't have any additional questions online, thank you very much for presenting and doing demo. I like demo at conferences, actually showing the stuff works. So we really appreciate this. And we will be back for the next talk, which will be presented by Peter from NVIDIA about UCX Spy. And after this, we have talk from AMD by Gabriel. And next sessions will start in 1:30 p.m. Pacific time, which is, I believe, roughly speaking, 1.5 hour break. Is this correct, Brian?
Correct. Pasha, we also do have one more question that just came in.
Okay, one more question. We have bonus questions that we just missed.
This one comes from Hessen. Will RNA lanes be related to RNDV lanes in any ways?
Sorry, what was the name? The second lanes, RNDB?
RNDV.
RNDV, okay. So it's actually the same. There are 2 types of RMA lanes. Actually, the whole terminology of RMA lanes is for protocols V1. There we had 2 kinds of RMA bandwidth lanes and regular RMA lanes. And RMA bandwidth is used both for a rendezvous protocol as a method to fetch the bulk data, and also for a RMA multi-rail that Sergey is doing now. In protocol V2, we're going to just remove those, and each protocol would have its own configuration of lanes.
Okay, I think that's the last one. All right, well, thank you, Sergey. So we're gonna go on a break, and then we'll be back again at 1:30 Pacific time.
Okay, it's 3:30. I believe we are ready to start. Our next presentation is by Peter and Chesef from NVIDIA. Peter is one of the drivers behind the UCX Spy, and this talk he'll present a new C++ backend for UCX Spy.
That's right. Thanks, Pasha, for the introduction. Similarly to previous years, before addressing the main topic of the talk, let me just give a brief overview of UCX Spy for the benefit of people who may be unfamiliar with it still. UCX Spy is a Python interface for UCX, providing an object-oriented synchronous API and a high-level asynchronous API for writing concurrent code with Python's async await syntax. No direct bindings to UCP are provided at the moment, and UCX Spy is intended to be a simple replacement for Python communications such as sockets, and thus would provide a similar interface, but it isn't identical to the Python sockets API. UCX Spy is targeted at library and framework developers, since Python users tend not to handle communication at the application layer directly. Because we provide a high-level library, no UCX or C knowledge is required to get started with UCX Spy, just a basic understanding of client-server communication workflows. Today, the largest consumer of UCX Spy still remains to be Dask, which is a framework for scalable analytics. And UCX Spy is normally made available to users via frameworks such as that. Still, for those who are potentially unfamiliar with UCX Spy, let me show another slide we presented in previous years to put in perspective the benefit of UCX Spy in Dask versus Python sockets. On the left, we see a workflow with the default Python sockets communication in Dask. And on the right, we see Dask using UCX Spy. In both cases, red represents communication. And with Python sockets, we see communication dominates runtime. But although communication is still non-negligible, even with UCX Spy, runtime is greatly reduced by replacing the original sockets-only communication backend. There are several reasons why we decided to try out moving the current UCX Spy implementation to C++, and here are some of the motivations for this large change. First and foremost is improving the performance of small messages. The existing UCX Spy implementation is also not thread safe, thus being a limiting factor for some use cases. The current UCX Spy implementation implements all C-based pieces in Cython. And Cython is great, but it has some shortcomings. For example, code can be significantly more complex than pure C or C++. For example, passing pointers generally requires typecasting any pointer to a uint pointer T or void pointer, and later back to its intended pointer type, which can quickly become very confusing. Cython also does not expose the complete standard library, which then passes the responsibility to the application developer, making the code longer and binaries larger. With C++ backend, we still use Cython, but only as a shim layer, exposing the C++ code in almost one-to-one API matching. We hope also that by having a C++ implementation, this will lower the entry barrier for new object-oriented language bindings and maybe even unify them all with the same underlying object-oriented implementation to expose a shim layer to the higher level languages, much like we are doing for Python now. Currently, the project is nicknamed UCXX as a combination of the UCX name with the CXX file extension that some of you may be familiar with, which is not a final name and open to suggestions as well. And from now on, I will refer to the new C++ backend and the project in general as UCXX. To exemplify some of the Python costs, let's consider the two code samples on this slide. On the left, we have async IO code. The async IO create task call wraps a synchronous function in an async IO future. Once the synchronous code completes, the state of that future is set with its result. By running a no-op function, we want to only time the cost of the future itself. Running this code, which consists of looping over 1 million iterations, and thus creates 1 million futures and await each of them, we see the total runtime is just under 12 seconds. On the right-hand side, we execute almost the same code, but without creating any futures, meaning the await call is just blocking on the call itself and not waiting for a future promise. Or in other words, it's fully synchronous code. This now takes just under 150 milliseconds. That is an overhead of about 80 times for using Python futures instead of pure synchronous code. So what we know so far is that async IO in Python is a large source of overhead. In the Stack Overflow discussion where we took the previous code from, the author presents 170x slower async IO usage when compared to the synchronous case. In our case, we only saw 80x, which is still far from non-negligible. That still means that the cost of waiting for one single future is in the range of dozens of microseconds, which is a critical overhead when many futures exist. That cost is also on a perfect scenario, of course, where the future is probably only awaited once, whereas in a real-world application like Dask, you may need to go over the event loop and check the same future multiple times. To cite a few of the possible solutions we considered so far, reducing the total number of tasks seems like a logical first step, which we'll discuss later on multi-buffer transfers. And reducing the overhead of async IO tasks will also be really useful, but it isn't clear whether this is even possible. Another alternative would be to replace async IO by something more efficient, for example, using UV Loop or Trio, which are libraries in Python. So these are possible alternatives, but potentially still not going to decrease the overhead by an order of magnitude or more, which is what we really need to get performance closer to the CUCX implementation, as we'll see later. There will certainly exist other improvements we could make from the Python perspective. Some of them we'll discuss on the slides coming up. And now I would like to begin by talking about some of the optimizations we added in UCXX. There are 4 primary optimizations or features, whatever we want to call them, and I'll address each one of them individually in a moment, but they are a UCP worker progress thread, delayed submission of message transfers, direct notification of Python futures from C++, and Python multi-buffer transfers. Let me begin by talking briefly about the UCP worker progress thread. As its name suggests, it really is just that, another CPU thread that progresses the worker. By taking control of that procedure, the thread is also responsible for setting the state of each UCXX request, including execution of their callbacks. It supports both progressing the worker continuously or in event-based mode by making use of the event file descriptor that can be requested from the UCP worker. Another optimization we introduce is delayed submission. That is another feature motivated from the Python world where we basically attempt to reduce the overhead of the color application as much as possible. Delayed submission consists in not fulfilling a transfer request immediately, but rather just registering the intent to do the transfer. In other words, it transforms all the transfer requests in minimal overhead, non-blocking calls. This requires the use of the UCP worker progress thread, which will execute submissions at the beginning of every iteration. Once again, this is motivated by the fact that Python requires to have the global interpreter lock, or GIL for short, for those familiar with Python, for every operation, meaning that no other Python operation can happen while some other operation is holding the GIL. In practice, what delayed submission does is to release the GIL as quickly as possible, even for transfers that would complete immediately, thus preventing the application to block even for short amounts of time, such as building, for example, the UCP structures for send and receive requests, as well as any other overhead involved. This in turn allows the UCP worker progress thread to only hold the GIL for the exact duration of notifying the Python interpreter that a request has completed. To illustrate how delayed submission works, consider the sequence of events on the screen. In this sample, we have 3 participants, the application thread running in Python, a C++ worker progress thread, and the submission pool, which is a thread-safe C++ container. This sample consists of the application thread submitting 2 transfer requests, S1 that will trigger immediate completion, and S2 that will require progressing the worker to complete. In both cases, the application thread does not submit the request via UCP tag send NB or UCP tag receive NB, but only registers the intent to either send or receive that message. Whether the call is sending or receiving a message does not matter in this case, or for this particular example, as the sequence of events would be the same for either case. After registering submissions, the next iteration of UCP worker progress thread will read all the submissions that have been registered and dispatch each one in the order that they were registered. In this example, particularly, it would dispatch S1, and immediately after it would notify the application of its completion, as progressing the worker wasn't necessary. On the other hand, S2 is enqueued, but not completed yet, so the UCP worker progress call would then run afterwards and then notify the application thread of completion. Use a more complex example. I know it's a bit small, but hopefully it can still be seen. This illustrates another hypothetical case where the order of events is less predictable due to the parallelism situation of both application and progress threads. What is still predictable, though, is the order the worker thread operates. First, it will read pending submissions. In the first case, they will be S1, S2, and S3, then submitting them in order and notifying the application of those that complete immediately. In the first case, that would be S2. And at the end, it would progress the worker and then notify the application thread of transfers that completed. So in this case would be S3 first. During the next iteration, pending submissions are read again, and the next iteration of the worker thread, that is, and this time only S4 is waiting to be dispatched. So it will dispatch it and finally notify the application thread of submissions that completed. In this case, S1 and S4 or S4 and S1 in order, and then the application is done in this case. So the Python notifier thread is another feature we introduced in an attempt to reduce the overhead of Python applications. This feature implements functionality directly in C++ that can be used from a separate Python thread to only notify Python futures returned by send and receive calls. Once again, another CPU thread is required, which will then take the Python GUIL and thus completely remove that requirement from the worker progress thread. The GUIL is also only required for that brief period of time to execute the proper CPython call used to notify a future of its completion. This thread is expected to sleep for most of the time, only waking up when there's one or more futures to be notified. To illustrate how the Python notifier thread operates, consider this diagram. In this case, notice that the worker progress thread is idle, so it could be even removed from this diagram, but I chose to keep it just for the sake of clarity. And this is perfectly fine, as the worker thread is not a requirement for the Python notifier thread to work. So in other words, we could still progress the worker from the application thread, for example, although this is not shown in the present diagram, just for simplicity. The usage of Python notifier thread requires an event loop to control all asynchronous events. So the application will begin by creating that resource first. Any asynchronous resource may only be used by a single event loop. So this feature can only work if the same event loop is used by both the application and the notifier threads. Thus, the event loop that was created must be registered and set by the notifier thread. Once the thread and event loop are set up, the application is ready to start. A typical use case would involve some transfer request being dispatched and progress if required. And the callback of the transfer request will then have an instruction to notify a Python future that it holds. So which is the return object when a Python transfer request occurs. So the future notify call will basically wake up the notifier thread, will ultimately notify the future via the event loop. Even though the worker progress isn't necessary for the Python notifier thread to function properly, they may be used together. The difference in this case is that the notify method of the future object is called from the worker progress thread, which will wake up the notifier thread and notify the future via the event loop, just like in the case we have seen previously. So basically, the only difference is who calls future notify, if it's whether the worker thread or the application thread. And the last feature we added is multi-buffer transfers. This is in some ways similar to IOV, but specifically aimed at resolving the following limitations. So first, allowing mixing CUDA and host memory in a single transfer. Work on top of the UCP layer, as IOV, as far as I understand it, is only supported by UCT currently, and providing the application with a single call and thus only one Python future per transfer operation. For that to work properly, the implementation needs some boilerplate code. The sender needs to first transfer a header with a predefined format containing the number of buffers, sizes, and types of each buffer that will follow. The receive will then parse that header and allocate memory appropriately. This requires the receive side implementation to know of the allocators for each memory type at compile time, though. which currently uses C, malloc, and free for host allocations, and the Rapids Memory Manager, usually more known as RMM, the device buffer class for CUDA allocations. And this is all, of course, possible to enable and disable via build flags. So neither Python nor RMM are hard requirements for the UCX, not for the C++ layer anyway. To put in perspective why all these features were implemented, we have a few plots here. To make fair comparisons, we are using only the TCP transport in UCX, which is also implemented by the Python Tornado library and using frameworks such as Dask to manage communications. To begin with, small transfers in Python are notoriously slow. This occurs by many factors, but it is primarily a problem when using the async IO programming paradigm in Python, as I mentioned in the beginning. On the left chart, we see that for small transfers, Tornado, or the brown line, is almost 10 times slower than the equivalent C code with UCX, the blue line. The orange and green lines represent UCXX and UCXPy core implementations, respectively. And by core, we mean here that they don't use asynchronous Python calls. And they are just marginally slower than the CUCX code. Finally, the red and purple lines represent the asynchronous implementation of UCXX and UCXPy, respectively. On the right plot, we see that latency is mostly constant for each of those implementations for small messages. This means that the transfers are in fact dominated by their implementation overheads. The reason why all this matters is that Dask relies heavily on small transfers for things like heartbeats and transferring information about the actual data being communicated, such as their sizes and number of frames. So we have an overhead also in the number of transfers that we execute before actually transferring the data that we care about. Now, let me show how the UCX implementation behaves in Dask. The UCXX implementation. The charts on the screen present bandwidth on the left and wall clock on the right for a QDF merge benchmark that is merging two distributed data frames. This is running on a single NVIDIA DGX1 with 8 GPUs, where some GPU pairs are interconnected with NVLink at 50 gigabytes per second or 25 gigabytes per second, or via InfiniBand at 12 gigabytes per second. So it has an heterogeneous topology. In this case, we are enabling all transports and not just TCP, as was the case on the previous slide. And we can see that average bandwidth has increased by utilizing UCXX when compared to the current public UCXPy implementation. This represents about 10 to 20% increase in the overall bandwidth. As for wall clock, we observe that for small chunk sizes, up to around 16 million rolls per GPU, we can get 5 to 20% reduction. But as we go beyond that, the curves flatten out. So that means that we don't have any further improvements for large chunk sizes, basically. This example is interesting because a QDF data frame may contain several buffers, one buffer per column, for example, which is where multi-buffer transfers may excel. When communicating all columns in a data frame, we then require only one Python feature, drastically reducing the number of asynchronous Python operations as the number of columns in that data frame increases. Now let's take a brief look at the main parts of the new UCXX C++ API. It is I believe it's important to first note one of the design choices made to use shared pointers to encapsulate virtually all of the UCXX objects. This allows the C++ implementation to pass the objects to other objects as well as among threads without requiring to move or copy. Moving and copying objects can be dangerous, particularly on asynchronous applications, as it's often difficult to reason about their state in any arbitrary point in time. Thus, using shared memory, shared pointers that won't allow moving or copying the underlying state seems the simplest and less error-prone option. Using smart pointers is also a great option to manage an object's lifetime, leaving little room for leaking resources. In this slide, we see some examples of how UCP objects may be instantiated from UCXX C++ API. First, the user needs to instantiate a UCP context, which can be done via the create context constructor in the UCXX namespace. It is also not shown in this slide, but the user is able to pass some arguments like UCX options that are can also be controlled via environment variables instead, and feature flags. And a context, as all of you know, is required to allow creation of further objects. So next, we are able to create a worker using the create worker method of the context shared pointer. I mean, the shared pointer to the context object, right? Also note that we are allowed to use the C++ auto keyword to automatically deduce the return type instead of typing that ourselves. Alternatively, there are constructors available in the namespace for all types, which may require passing the parent object as an argument. For example, there's also a create worker constructor that takes a context object to create the worker, which is equivalent to the code just above. So the create worker method and constructor create a UCP worker under the hood. Similarly, there is a create listener method in the worker object that takes a port to bind the listener to, a callback function, and arguments that the listener will execute when a client is connected. And this method obviously create a UCP listener. Endpoints can be created from 3 different methods or constructors. They are create endpoint from hostname that connects to a listener, passing a hostname or IP address along the port. Along with the port the listener is bound to. Create endpoint from worker address, which connects directly to a remote worker via its address. And create endpoint from con request used from the listener callback to create a connection to the remote client that is initiating that connection. All those methods derive directly from the existing UCXPy API, and of course are not final and subject to change. And of course, please feel free to connect with me if you have any suggestions or requests to make the API more robust, if you can visualize some nice uses for it. The transfer API should be very straightforward as well. From an endpoint, the user should be able to call tag send and tag receive for tag operations, receiving a pointer, size of the buffer in bytes, and the tag, which should be matched. Similarly, the string API is also available. Besides being named stream send and stream receive, they do not receive tags to be matched. Among some of the methods to query state and operate on requests, the isCompleted method will return whether the request has already completed. And in the positive case, the user may use check error to verify if it completed successfully or if an error occurred, in which case check error will raise an exception. Alternatively, the getStatus method will return the UCS status T value of the request, and no exceptions will be raised then. A request can also be canceled before completion with the cancel method. And we can now move forward to take a look at a brief sample application combining the API we saw. This sample consists of creating a UCXX context followed by a worker, and then starting the progress thread. Progress thread will take care of spawning the thread in the mode of choice. The default is event-based, but polling can also be set via the argument that method takes. Then we create two endpoints for simplicity in this example. They are both using the same worker. And we then allocate send vectors of integers containing a range of 8 elements and an unfilled buffer with the same type and size. Now we are ready to transfer data. In this example, we simply send the buffer on EP1 and receive it back on EP2. Note that we use a single vector of requests, which is then awaited in a single call to the wait requests helper function. It is not shown in here, but what it does, it will look through requests, checking them for completion, and if they all succeeded in the end or not, and in that case, raise exceptions. And it is nevertheless possible to await each request individually should the application require so. Now, the Python core API is very close to the C++ API. This sample is equivalent to the one we just saw on the previous slide. We begin by creating context, worker, and starting the worker progress thread. Following, we create the same two endpoints that will send and receive data. And because Python does not allow direct buffer allocation via malloc or new, for example, we need to use some library that allows allocating some type of memory. For UCXPy and UCXX, the library used must support the Python buffer protocol for host allocations or the CUDA array interface for CUDA allocations. From the buffer protocol and CUDA array interface, we are able to get the underlying buffer pointer, which we then may pass to the C++ transfer calls in UCXX. In this example, we chose NumPy to create a range of type int32 with a length of 8 elements and an empty array with the same type and length to receive. We then are able to request and store the requests on a list, and then wait request is used to implement the same sort of operation we have seen in the previous example to verify whether each of the requests has completed and finally raise errors if not. Now, the async Python API is significantly different. The user is not responsible for managing contexts and workers and can immediately begin by instantiating endpoints. Following that, we allocate the same NumPy arrays as we did previously. Now, the part that behaves very differently than the previous examples is doing the transfer requests. The send and receive methods return Python futures, which can be awaited individually or as a list using the async IO gather method. This is where we have significant overhead for short messages, which we are trying to optimize as much as possible. And the API remains almost entirely identical to the current UCXPy implementation. So very little will need to be done by end users to adapt, namely on how they will progress the UCP worker. Most likely only that will be necessary. Another thing that is a little different is that force tag argument, which has the purpose of using the tag specified by the tag keyword argument without any modifications. As internally, UCXPy the UCX by implementation of send and receive in the async IO implementation try to simplify things for the user. So the two endpoints that get established will predetermine random tags at the point in time where the connection is established, in which case the user also does not need to care about passing a tag at all. If we wait for the futures and they complete successfully here, the code will simply continue. If not, it will also raise an exception for failed transfers. From the async Python API, we can also do multi-buffer transfers, as explained previously. The main differences here are that we use a send multi and receive multi methods. And instead of passing a single buffer to the send multi, we pass a list of buffers and no buffers at all to the receive multi call. The send message object here is simply a list of 8 int32 buffers, each with a length of 8 elements. We could also mix any different sizes and also host and CUDA buffers in any order. To receive the message, we didn't pass any buffers to the method, and that is because we don't have any prior knowledge about the message we are about to receive. Due to that, the receive multi call needs to do all the allocations internally, as I mentioned in a few slides back, independent of whether they are host or CUDA memory being transferred. When calling receive multi, that operation will return a list. In here, represented in this example, represented by the receive message object with the same number of buffers of the send message. Note that it is possible to use multi-buffer transfers directly from C++, but that can be thought of more as a convenience function rather than an optimization, because the exact same behavior and performance could be achieved by user code without a lot of additional work. So to conclude, this is the current state of UCXX. Currently, we are working with C++ 17 as a requirement, mainly because of CUDA support, as RMM only supports C++ 17 and above. At this point in time, we could still potentially revert that to support C++ 14 as well, without too much work, but that would depend on user demand. Some features from UCXPy that are not used in Desk are still missing, such as parts of UCP address, RMA, and active messages. Also, documentation is still unfinished and requires a bit more polishing work. We intend to provide CMake support. This mainly comes from the fact that Rapid's team uses CMake for all C++ projects and have already great support for CUDA, for UCX, and other projects, which would make it simpler to port over to UCXX. We haven't had much code review yet, so we will still have a thorough review before publishing the code, of course. It hasn't still been decided how this code will be published, if on the UCXPy repository as a new backend version to allow phasing out the old one first, or as a new repository. In either case, the intent is that this will be upstream to the UCX repository. And by now using C++ for the bulk of the code, we hope it will also be easier for UCX maintainers to understand the code and make modifications when necessary, without necessarily any deep knowledge of Python. And finally, we believe the code is already usable and hope that will still be made available in 2022. But this is subject to schedule changes, given this is still missing some content and tasks that I just discussed. And yeah, with that, I conclude the presentation, and we'll try to answer any questions if we have any. Thank you.
Great. Thank you, Peter. Appreciate the presentation. Just a reminder to the attendees, you can ask questions either the chat panel or through the Q&A panel that's located there at the very bottom of your screen. Panelists, if you'd like to ask a question, feel free to unmute yourself and go ahead and ask Peter. Peter, I do have one question. Just, you touched on it there at the conclusion in terms of merging things in to UCX Pi. What do you think is going to be the overall deciding factor of whether that's going to happen or not?
Basically ourselves, I think. I've been mostly driving this work, and I think we can do whatever we want. It's just a matter of how we want to phase this out, because this is on a separate private repository currently. And so one way would be to just drop everything in, but that's quite a lot of code, or creating a new repository with all the history of changes and everything that will maybe make things simpler. But I think we don't have any hard constraints on either way. So it's up to us to decide. So I think it just hasn't been discussed thoroughly yet how to do it.
Okay, understand. Do have one question come in from Hessen. He says, does the C++ API have support for active messages in RMA?
No, not yet. This is what I think I mentioned in the last slide, right? So this is still not implemented, but just because I didn't have time to do so, but they will be implemented.
Okay. I don't see any of the other panelists unmuting themselves, so I think that we are good to go. Thank you again, Peter. Appreciate your time today.
No problem. Just, I think there's one more question.
Oh,
is there a worker?
You're right.
Yeah.
Is there a worker progress?
Yeah, there is a worker progress, and the user is free to choose. There is a worker progress. You can also use the, I don't use that too often, but it's supported. I don't recall if it's wait progress or, yeah, but we support basically all types of progressing, so the user is free to choose. I just didn't have time to show everything here, but it is supported, yes. You can worker progress like in a loop and just do it in a basically polling mode, or you could progress via event-based. Yeah. Also, just to answer what Yossi mentioned there, maybe call it UCXPD, but I actually thought about UCPP as well, because then it would be, because we currently only expose UCP, the UCP layer, so UCPP, right? So that is also open. I don't have a specific preference in mind so far. I just went with UCXX for whatever reason now, but it's open to suggestions.
Actually, I have another comment. So you chose to expose tag API, but actually we don't recommend using tag API outside of MPI, because there are a few inherent issues with this API with regards to error handling. So for example, if there is a multi-fragment message that is not fully meshed, and then the endpoint is destroyed, the endpoint that's supposed to receive it is destroyed, then some descriptors could remain on the matching queue, and there's no good way to solve it. So I guess the applications that are going to use this API are not going to be MPI, going to be that driven application that would eventually require some kind of error handling support. So
yeah,
I recommend.
There is already error handling. I don't know if you recall, but this is something that I've worked extensively with Dmitry to resolve, like many of these kind of issues that we had in Dask with endpoint error handling, and Dmitry has implemented a ton of different fixes there to allow us to work with tag, because at the time that UCX Pi started, there was no active messages. So we were basically using tag API since, and even in UCXPy, there is already active messages support, but it's a little bit slower than tag. So I haven't taken so much time to actually go through why that happens. But yeah, the overall idea for Desk is that we eventually switch to the active messages API. But just now it was easier to work with the tag API because I knew how it worked already in Desk.
Okay, thanks.
All right. Thank you again, Peter.
Thank you.
All right. Our next presentation and our last one for the day comes from Edgar Gabriel from AMD. Edgar, how are you today?
I'm pretty good, thank you.
Fantastic. Edgar is one of the original authors of the OpenMPI library and continues to be the main architect and maintainer of OpenMPI. Today, he's going to be talking about AMD's Instinct TM, the MI series accelerators, and the ROCm software stack in the UCX ecosystem.
Yes, let me try to. All right. Can you see my slides?
Yeah, looks great. Thank you, Edgar.
All right. So what I would like to do is basically give something like a state of the union on how to use AMD GPUs in the UCX ecosystem for communication operations. And I will touch on a number of communication libraries because of that. Oops, that was too fast. I will talk a bit about UCX, UCC, OpenMPI, and MPICH. So let's get started. UCX, let's start out with what is the current ROCm support in UCX as of today. So we have two UCT components available. The copy component that basically implements data transfer between host and device memory within a single process. The IPC component that performs data transfer between device memories of different processes, but within the same node. There is also GPU direct RDMA support for data transfer between device memories of processes on different nodes. So these three aspects fundamentally basically, or these three components implement the data transfer between various processes, typically in MPI scenarios, but also beyond that if required. We need to have, in addition for these operations to perform successfully, we need to have, of course, memory type detection. And we do also have support for memory hooks to intercept ROCm memory allocations. Now, from the implementation perspective, these operations are implemented on top of the ROCm runtime layer, so the rocker layer, and not on the HIP layer. HIP is the programming model, but it's internally also implemented on top of the ROCm runtime layer. And the advantage for us is, from that perspective, is really that the memory hooks provide a much simpler interface, for example, for memory allocations on what we need to intercept and how we need to deal with it, compared to like a wide range of potential memory allocations available in the programming model itself. Now, a couple of words on some of the things that we've been working on over the last year or so. So the runtime layer API functionalities, for example, for data transfer operations, have the notion of a agent. That think of the agent as the hardware unit that basically manages a particular memory address. So, for example, this can be like the GPU that was used to allocate a certain memory region on the GPU device, but this can also be a host. And so we had to rework there, or we did rework there, the logic on how to determine the various agents for source and destination buffers. The agent selection itself has an impact on what type of hardware is used for the data transfer operation itself. Think of it this way: if you would have two host buffers, just as an example, you would not want to use any GPU resources for the data transfer operations, while the other way around, of course, it's also true that if you have two GPU buffers, you probably don't want to use any agents that are capable of handling CPU resources, right? Part of the challenge, of course, is that a single process might not be able to see all devices, since the user might have restricted the list of available devices from a single process's perspective using the rocker visible devices, or there's also a hip visible devices environment variable, right? So you basically have to have the proper selection, but also a fallback mechanism available. We performed also some work on the memory type detection part, on how to distinguish between the device versus unified versus host memory. And so this is a surprisingly complex topic because it can also depend on the Linux kernel that is being used, etc. But the biggest change really probably was that we used to have two different locations where the memory detection has been done, namely the memory hooks part of the code, as well as the ROCm UCT layer itself, and we simplified it and unified it to a single memory, to single code location, which simplifies code management. We invested quite some time in validation and tuning of our newest GPUs, the MI250X, to make sure that it works without any major surprises from the end user's perspective. And last aspect that I want to mention here briefly is that we've recently introduced new options for the short protocol in ROCm copy. And let me give you here a little bit of an explanation. So fundamentally, with AMD GPUs, the host can always access any GPU memory address. It's because of the PCIe large bar support setup, you could execute a memcopy from the host onto a GPU address. This is what we refer to as a host-triggered copy operation. You can, of course, however, also use runtime library copy operations. And the Z-copy protocols in ROCm have used for quite some time now both methods with a threshold when to switch from one copy mechanism to another copy mechanism. So the threshold when to switch from host triggered operation to runtime library copy operation depends on the copy direction, like device to host versus host to device. It depends on the device type, etc. And again, as I mentioned, the Z-copy protocol operations used to do that for quite some time. The short protocols didn't used to do that. The short protocols only implemented or were based on the host triggered operations. Now, the tricky part there, of course, is that the short protocol is not necessarily just invoked for message length that we considered optimal for host triggered operations. So we basically implementing now the same two-stage protocol or two mechanisms for short protocols as well. And as you can see on this graph that I've attached to this slide, so basically having the ability to use now also the runtime library copy operations for short operations can lead to quite some performance improvements as well, because the short operation is not just used for short messages. It can be like a building block or something that is being invoked by the various rendezvous schemes in different scenarios as well. So the impact can be quite significant. So that's all I had to say for UCX. Let's say a couple of words to UCC. So there will be tomorrow a long session on UCC, so I will not go into the details on what UCC is and how UCC works, etc. But let me just add briefly that we did add support for AMD GPUs earlier this spring as well. So this consists of a MC component that manages ROCm memory management in UCC. This contains an EC component which basically executes operations on ROCm memory, and that includes data transfer and reduction operations. And finally, I mean, the execution of collective operations in UCC can be based on two different team layers or team layer components, namely the RICL component, that's the AMD ROCm collective communication library that is available, but also the more generic TLUCP component, which by itself is memory type agnostic, but basically because of that can also invoke the correct MC and EC components for any memory type that is identified and available. I will focus for the next couple of slides on TLUCP because I think this is more in line with the context of this workshop. And one thing that I would like to bring up again here or discuss here is how important it is that the UCC library has the ability to recognize and manage different memory types. The important aspect or interesting aspect of that is, however, that recognizing a particular memory type is not equally important or necessary for each collective operation in itself. Respectively, let's put it this way, the impact will be bigger for some operations than for other ones. And to give you an example, let's start out with talking about broadcast for a minute. If UCX has been compiled with ROCm support and you are now executing something like a broadcast operation on GPU buffers, UCX will perform the data transfer operations on your behalf without any problems. So you can just take the call tuned component of OpenMPI, for example, and you will have data transfers between devices or between device and host memories, whatever your configuration is, and that will work just out of the box, right? So if you do that, what you see here is basically a comparison of call tuned versus using call UCC in OpenMPI with the UCPTL. I've normalized the execution times to the values obtained with call tuned. It's a 64 processes test case using 64 GPUs. And I mean, it makes logically sense that for an operation that purely performs data movements, it will, in this case, really come down to just purely algorithmic aspects on who does what, which component does what to implement a particular operation, right? And you see that there are scenarios where UCP is better versus tune and vice versa. The situation is, however, quite different for reduction operations. And the important aspect here really is that if the communication library or the collective communication library is not memory type aware, reduction operations require temporary buffers. Think of something like a binary tree where you might have to receive the data from a different node to perform the reduction on or combine the two, your own data buffer with the data buffer that you receive from the other node. Now, if your collective communication library is not memory type aware, you could just perform a host buffer always, right? And now you have the problem that your input buffer might be on the GPU, but your temporary buffer that you are using for the reduction is on the host. In case of our GPUs, this will still work because you can perform load store operations on a GPU memory address. But now the performance penalty of performing the load store operation from the GPU into a host buffer, performing the reduction operation, and then storing the result onto the GPU buffer again, this will be now quite significant. And as you can see on the graph over here, let's focus first on the large message sizes. You see that here, this is really where the architecture of UCC is simply highly beneficial for GPUs because it can allocate a temporary buffer on the GPU. It launches a GPU kernel to perform the reduction operation in itself, and you obtain orders of magnitude better performance than if you use algorithms that are not or component that is not memory type aware. Now, there is, however, one more little detail that I want to show and discuss here as well, and that's the short message sizes that you see on this graph. So for 8 bytes up to, I don't know, maybe 128 bytes, you see that UCC is is slower than if you would perform the operation just purely on the cold tuned component. And this overhead is really simply from the fact that launching a kernel takes some time, right? And this is now something that we are working on how to deal with that. And what we have right now is we've extended our EC ROCm component to be able to perform also reduction operations on the host, even for GPU buffers. And again, we don't have to copy explicitly the data from the GPU to the host, because the host can access and perform load store operations on GPU memory addresses. And we simply, in this case, now avoid the kernel launch latencies. So the expectation is not that this is a mechanism that will help you scale up for large message sizes, but for short messages, you basically can avoid the costs of the kernel launch. And maybe more importantly, if you have a scenario where the user is running a compute operation or a compute kernel on the GPU, you might be able to perform in parallel a reduction operation, even if the data is in GPU buffers, without having to interfere with a compute operation occurring on the GPU. And this is what I'm showing in this graph. So basically, this is an all-reduced overlap benchmark. We have a kernel that fully saturates the GPU, right? And at the same time, we would like to perform a reduction operation, a short reduction operation on data that is residing in the GPU. And using this new feature, basically, you can see that, yeah, you can reduce the execution time of a short reduction operation quite significantly by using this mechanism. Now, this part is not yet merged into UCC. There's a pull request pending, and I think it will hopefully be merged within the next couple of weeks. But yeah, it shows quite some benefits and is an interesting feature, taking advantage of something that our GPUs offer. Now, this is all I had to say for UCC. So let's try to put now all of these pieces together. So we have basically UCX for point-to-point operations, UCC for collective operations. How can we bring all of this together in an MPI library? So OpenMPI offered support for ROCm devices through UCX, specifically the UCX PML for two-sided communication, and the OSC UCX component for one-sided communication. We added earlier this spring support for ROCm devices into OpenMPI, which includes things like the configure logic to detect the ROCm software stack, code for ROCm memory type detection, as well as data transfer operations to and from ROCm devices, which is at this point beneficial for non-contiguous derived data types. This is committed into OpenMPI as well as the current 5.0 release branch. So you will basically be able to add a dash with ROCm flag to your configure line in addition to UCX and UCC. And you should see some performance improvements, especially for derived data types. I will show some results on the next slides. What else is included in this commit is basically also a function to query support for the ROCm software stack within the OpenMPI library. And not part of OpenMPI, but basically part of this process was also developing a systematic HIP-MPI test suite that we can run to evaluate various features and functionality. Now, it's probably not a big surprise, but basically, again, derived data types, before we added support into OpenMPI for ROCm memory versus once this support was available, is of course quite beneficial. Again, because of the way the AMD GPUs are set up, things worked also prior to this commit because you could just do memcopy operations. But depending on the data type itself, if you had like large blocks of non-contiguous data, the performance, there will be quite significant performance benefits in using this new feature versus what was there previously. Again, I mean, how strong the benefit is depends a bit on the type of your data type, on your application scenario, etc. But this is showing quite some performance improvements in many cases. More interestingly, probably, however, from that perspective, is some work that is currently still ongoing in OpenMPI. So there is currently work on introducing a new framework that basically abstracts out GPU utilization in OpenMPI. I would like to give here credit to the group that performs most of this work there, and that's Amazon. The key benefit, I think, from the OpenMPI perspective really is that it reduces GPU vendor-specific code sections. So right now, if you look into the main repository, you might have quite a bit of code sections where it says if they have CUDA or if they have ROCm, right? And this approach simply is not very scalable with a number of GPU vendors potentially being available. So this framework now basically abstracts these operations away. You can reduce these specific if-defs in the code part itself. This is probably the biggest advantage overall. Now, in theory, OpenMPI can now also be compiled supporting multiple GPU vendors simultaneously. I'm not sure that's of big interest for an individual data center or compute facility that basically compiles their MPI libraries themselves, but it could be something interesting for Linux packagers, because they might not have to provide different MPI libraries for supporting the various GPUs available on the market at the moment, right? If this is done, if somebody would compile OpenMPI supporting, for example, the CUDA and the ROCm software stack simultaneously, then the runtime selection logic of the accelerator framework will identify at runtime what hardware has been found and select the proper component at that time. There's, of course, the restriction that only one GPU type vendor is allowed per node. But at least in theory, that would not prevent somebody to use different GPU types on different nodes. Again, not sure whether that's of interest, but technically I think that could potentially work. So the current status of the accelerator framework, so there are components for CUDA and ROCm being implemented. There is a target to include it into the 5.0 release, but there's currently also still some work ongoing on the internal APIs of the accelerator framework and a couple of other organizational issues there. So we'll have to see whether it will actually make it into OpenMPI 5.0 or whether it will have to be the next release. But yeah, so I think this is really interesting work with potential for quite a couple of additional optimizations in the future. Just to mention one more item that is part of the accelerator framework, and maybe we are not yet exploiting it the way we could, is that it has support for 2D memcopy operations, right? And I think, so if you would have like certain derived data types like subarrays or type indexed, you could map that now to a two-dimensional memcopy operation, which is performance-wise significantly faster than using the 1D memcopy operations that we have so far. So the interfaces are there. We are just simply not taking yet advantage of that. Now, let me also say a couple of words to MPICH. So MPICH does also support ROCm devices through UCX. So basically, you're doing much of the same things like with OpenMPI. You have the -- with UCX option to provide your UCX installation directory, and you need to provide with a -- with HIP option the directory of the ROCm software stack, and maybe provide the target GPU architecture for which to compile the required HIP code. there's tomorrow also a session on MPICH, so I will not share and will not say much more to that. Maybe except for one interesting little detail. When querying support for AMD GPUs, so the work done by the MPICH group and the Open MPI group were done completely independent of each other, and MPICH has a function called MPIX query HIP support, while OpenMPI has a function called MPIX query ROCM support. And if anything, I think this just highlights the necessity for standardizing these interfaces, and there is a pull request or an issue that will be discussed next week in the OpenMPI forum that hopefully addresses some of these issues, because for end users, I mean, they want to have a portable way on how to retrieve this type of information without having to have MPI library specific knowledge on what is the precise function name for that operation. That's all I really had to say. In summary, I think with UCX, UCC, and the integrations of OpenMPI and MPICH, users have good support for our hardware platforms at the moment. And if there are any questions, I would be happy to answer them.
Thank you, Edgar. Just a reminder, you can ask questions through the Q&A panel at the very bottom of your screen, or you can ask in chat. If anyone in our panel would like to unmute themselves and ask Edgar a question, you can do so now. Just give it a moment here, Edgar.
Yeah.
Okay, well, I'll say that's no questions at this time. So thank you again, Edgar. Really appreciate the presentation.
Thank you very much. Yeah.
Fantastic. Well, everyone, this concludes day one of the UCF conference. Look forward to seeing you on day two. It starts tomorrow at 8 a.m. Pacific. Hopefully you have that Zoom registration. Each day requires its own login. We look forward to seeing you tomorrow morning. Thank you.